Good afternoon, everyone. How's everyone doing? Good. Woo! So my name is Manojit Nandi. I am a senior data scientist at Microsoft Research, and thank you for coming to this tutorial, Assessing and Mitigating Unfairness in AI Systems. Hopefully you're all in the right place. Hopefully you're not meant to be at that gymnastics, tumbling, and trampoline event. But if you are meant to be at that event, I'm sure you can just get there with 1 or 2 handsprings. So with this tutorial, we have 2 different setup options. One is that I recommend. One is either just using a Google Colab notebook. Another thing you could do is actually set up a Conda environment. And I recommend if you are planning to use a Google Colab notebook to install the libraries right now. It does actually take a couple of minutes to run the setup instructions if you are doing the Google Colab. There's also a weird not a hiccup, but I guess just because of how Google Colab is set up, that after you do these library setups, you'll need to restart the environment. That's just so that the Colab can load the right packages beforehand. So I'm going to be running this locally, so I'm going to skip this first step, but if you are doing this with the Google Colab notebook, you should run this cell. If you are doing a local run, you don't need to install these right here. And so I guess let's get started. So as a brief introduction of Fairlearn and other resources I'll be covering in this tutorial. So this tutorial builds on various different open source projects. We use common machine learning and data processing libraries such as scikit-learn, pandas, NumPy. We also use various data visualization and plotting libraries such as matplotlib and seaborn. And then in particular in the space of responsible AI and fair AI, we'll be using a library called Fairlearn and also the Model Card Toolkit. So chances are you've probably heard of the first 5 libraries, but these last 2 libraries will be new to you. So to give a brief introduction of what these are, Fairlearn is an open source, community-driven project to help data scientists assess and improve the fairness of their AI and machine learning models. We include a Python library that allows for fairness assessments and also provides different techniques for unfairness mitigations as well as visualization of fairness metrics. We also provide educational resources that cover both like the technical aspects of AI fairness, but also some of these socio-technical aspects, such as the organizational parts of this. How do you sort of talk to your manager or talk to your CEO about, hey, why should we care about AI fairness? Why should this be a thing we should be investing money and headcount and resources in? And the Fairlearn project was started in 2018 out of Microsoft Research. But last year in 2021, we adopted a neutral governance structure, and since then has been a completely community-driven project. We have community members in the audience, and also we have another community member giving a talk at the PyCon Charlas tracks. So if you are interested in learning more about Fairlearn, but in Spanish, I do recommend you check out her talk on Saturday. In addition, we'll also be using the Model Card Toolkit. The Model Card Toolkit streamlines and automates the generation of model cards, which are these documents that provide context and transparency about a machine learning model, how it was developed, and how it should be deployed, and what situations should you not deploy that model. This was released by Google in 2020 and is still maintained by Google. So before we dive into the main part of this tutorial, I'm going to start with a brief overview of fairness in AI systems. This will be about like 25 minutes. So if you've read anything in the news in the past decade, you might have heard that we're living in the age of AI, this era of big data. And every week there comes out a new story about some application of AI and machine learning that will completely revolutionize the world. We'll have computer systems that can take in text and automatically generate images. We have stories about progress in self-driving cars. But at the same time, with all these stories, we also hear news stories about AI and machine learning systems gone wrong. We hear stories about how a machine learning system has marginalized or harmed a group of people. And these stories really highlight why it's important that when we build these systems, we get it right. We make sure that the AI systems we build do not discriminate or further disadvantage already disadvantaged or historically marginalized groups of people. And so some stories in the media you may have heard of may involve situations where an AI system was used to make a high-stake decision. such as allocating opportunities or resources. For example, there's this famous story of the COMPAS algorithm. And so in 2016, ProPublica investigation showed that this algorithm COMPAS, which was used to decide recidivism risk scores, incorrectly scored black defendants as high risk compared to white defendants. And so what this system was used for is by judges, when they're deciding to give a detained prisoner a bail, they'll basically say, what's the likelihood that this prisoner, if given bail, will go on to reoffend or commit another crime if they're released? If that risk score is high, then they'll probably not be given bail. If that risk score is low, then that increases their chance of being given bail. And this system found that that COMPAS algorithm incorrectly gives black defendants much higher risk scores, so it says that they're more likely to reoffend compared to white defendants. In addition, it also said that white defendants were more low risk than they actually were. And so here's an example of the COMPAS algorithm. It takes an individual, it sort of assigns a risk score from 1 to 10. Higher numbers means more risky. But on the other hand, there have also been other news stories that have involved more mundane examples. For example, researchers at Princeton have found that translating sentences such as he is a nurse and she is a doctor into Turkish, which is a gender-neutral language. Turkish does not have gendered pronouns like he, she, he, him, or she, her. And then when you translate that back into English, yielded more stereotypical and also incorrect translations of she is a nurse and he is a doctor. And examples like this sort of showcases like all the idiosyncrasies of how fairness is very difficult to do in practice. And actually with this example, Google has actually sort of addressed this issue by allowing for gender-neutral translations when you go from non-gender to gendered languages. So if you go from Turkish, this person is a doctor, you would get back both he is a doctor and she is a doctor. And the key thing about fairness is that it is a socio-technical challenge. And what that means is that even though we can spot fairness-related harms, when we see them, there's really no one-size-fits-all definition of fairness that can apply to all AI machine learning systems across all contexts. Fairness in AI is inherently a socio-technical challenge, so you can't solve this purely from a technical perspective or from a purely social perspective. You need some combination of both sociological thinking and sort of understanding the context in which your system will be deployed in, but also an understanding of the system itself. And this makes it kind of difficult a difficult topic to navigate. But although there are very few easy answers, I think there is a variety of emerging strategies and tools for assessing and mitigating fairness-related harms, as well as a deepening understanding of how technology is sort of embedded within our society. And one key thing about the Fairlearn community is that we want to avoid using this term, bias. And now if you've read anything about fairness in AI and machine learning, you've probably heard this term bias be thrown around a lot. This system is biased. We need to debias the system. But it's often used as this catch-all way to describe any unfair behavior of an AI system and the also possible causes of that unfair behavior. However, we want to avoid using this term bias when possible. It's a very ambiguous term. And there's also a lot of different definitions of bias, such as statistical bias versus like societal biases. And instead, we want to use the term fairness. We want to talk about, instead of talking about bias, and we want to talk about fairness-related harms. We want to focus on the impact that a system can have on people. That is the specific type of harm that the system is inflicting on a group of people. And that gives us a very useful thing, because by focusing on the type of harm and who is being harmed, we can better think about what mitigations and strategies we want to deploy. By centering the conversation about who is being harmed and how can we help them, we can better think our mitigation strategy rather than focusing the conversation on this algorithm is biased and we need to debias this algorithm. And I also want to emphasize that in addition to avoiding the term bias, I want to recommend that you avoid using this term debiasing as well. I think using this term debiasing a system or debiasing algorithm really sets up for very unrealistic expectations that, oh, you have this system and all you have to do is just pull out the bias of it and then it'll be perfectly fine, which is a very bad way to think about this. Rather, we want to be thinking about fairness-related harms, and we want to talk about mitigating those fairness-related harms. The reason that this is a big issue is because these algorithms cause harm to people, and we want to think about how can we mitigate the harms they experience, and how can we help those people. And since we'll be talking about algorithmic harms, I think we need a language for talking about those types of algorithmic harms. And so, broadly speaking, there are really 5 major types of fairness-related harms that are caused by an AI system. These 5 are allocation, quality of service, stereotyping, demeaning, and over and under representation. And so I'll be running through a brief examples to sort of highlight what each of these types of harm mean. And one key thing to note is that while there are these 5 types of harms, this is not an exhaustive list. As we continue to develop new applications of machine learning and AI, we'll probably come up with systems that can produce new types of harms. And another thing is that these harms are not mutually exclusive. A singular system can inflict multiple types of harms, and it can also introduce different harms to different groups of people. So the first type of harm we want to talk about is this harm of allocation. Does the system allocate opportunities or resources in a way that negatively impacts a group of people? And so when you hear about AI fairness in the news, this is the most common types of stories you hear about, where the system has been used to allocate opportunities or resources in a way that negatively impacts people's lives. For example, there's this very famous news story where Amazon had to abandon its automated resume screening tool after it found that the system sort of amplified existing gender imbalances in the tech industry by withholding employment from women. And so what they did is that Amazon has this tool, it screened people's resumes, and what it was finding is that it would discriminate against women for things such as saying, I was in the president of the women's chess club at my college, or I was on the women's lacrosse team. And it would downweight those for which makes no sense, because it's like, why would you penalize for someone for that? And so in this case, the system is sort of unfairly allocating resources or sort of withholding opportunities or job opportunities from women in the tech workforce. The next type of harm is a quality of service harm. And so quality of service harms focus on whether an AI system works very well for one group of person as it does for others, even if no opportunities or resources are withheld. And there's this very famous example in which researchers at MIT, Joy Buolamwini and Timnit Gebru, found that commercial facial recognition systems achieved a much higher error rate on darker-skinned women compared to lighter-skinned men. And so what they did is they did an audit, and they found that if you upload a picture of a face of a darker-skinned woman to these commercial facial recognition systems, that the system was more likely to miss their face or say that there's no face present in the photo compared to lighter-skinned men. And this is actually a very famous example. This is actually a Netflix documentary called Coded Bias about Joy Buolamwini's work that she's done over the past few years. And it's a very interesting example, because if you look at the error rates present, you would find that the difference between the error rates in the darker-skinned females versus lighter-skinned males is about 20 to 30% on average. And that's kind of incredible if you think about it. What that means is for these commercial facial recognition systems, if you upload a picture of a darker-skinned woman, there's a 1 in 3 chance they won't detect their face. And like accessibility issues, quality of service harms can raise questions about respect, dignity, and personhood. Imagine how someone would feel if a voice recognition system failed to recognize their voice, but recognized the voices of their peers very easily. And the next 3 types of harms are collectively called representational harms. They're typically associated with natural language or computer vision, like the deep learning-esque problems. And the third type of harm is stereotyping harm. This harm occurs when a system promotes or reinforces harmful or negative stereotypes about a group of people. And so Latanya Sweeney showed that online advertisements were more likely to suggest that people with black-sounding names have been arrested compared to individuals. If you search your name and you have a black-sounding name versus if you Google your name and you have a white-sounding name, the ads return would basically more likely say so that this person has been arrested if you enter in a black-sounding name, and therefore reinforcing negative stereotypes about the black community and black criminality. The fourth type of harm is harm of demeaning. And so this occurs when an AI system is actively demeaning. And so when it was first launched in 2015, Google Photos had this very infamous example where a group of black teens uploaded a selfie at a graduation party, and Google Photos like auto image captioning or auto image labeling tool sort of labeled that selfie as gorillas. And so this label is really, really bad. Like, not only is it wrong in the technical sense, but it is demeaning. It is reinforcing and using a harmful label that has been applied to black individuals in Western countries for years. And finally, the last type of harm I want to talk about is sort of this harm of over and underrepresentation. Do systems over or underrepresent certain groups of people, or possibly erase groups of people entirely? And so researchers at University of Washington examined the image search results for professions with an equal or higher number of men compared to women, such as engineering. And what they found is that these results were heavily skewed to men, far more than reality. So if you Google something like engineers, or if you Google CEO, you're more likely to actually get just entire pictures of white men. There's a very famous thing about this. If you how long do you have to scroll to get the first picture of a woman CEO? And it takes about 100 images, and that first woman is CEO Barbie. And so, just to recap what I just talked about in the last couple of minutes, there are really 5 main types of harms that can be caused by an AI system. And these harms are not mutually exclusive. A system can cause multiple types of harms, and it can exhibit different types of harms to people. For example, in some of these examples that I talked about, you can see things that the automated system that does not rank women as highly for men for technical jobs is both producing an allocation harm, it's producing a quality of service harm in that it's not working as well for women compared to men, it's promoting harmful stereotypes against women, but it also leads to over and underrepresentation. If the system is filtering out women at a much higher rate than men, that's going to lead to more men filling these technical positions at Amazon, and thus overrepresenting men in the technical workforce. One also important thing to keep in mind is this idea of intersectionality, and that is the idea that people at the intersection of different demographic groups are more likely to experience harms compared to just the individual groups. And so going back to this example of these commercial facial detection system, the individuals at the intersection of being darker skinned and female will more likely experience these harms that are not experienced just by darker skinned male, but also by lighter skinned females. And so by thinking about the individuals at this intersection of these groups, that allows us to better think about who could be harmed, as it produces new ways that people could be harmed that were not just obvious by looking at a single demographic group. And so now we're going to jump into this healthcare scenario that we're going to be working through the rest of this tutorial. And so our scenario sort of builds on previous research that highlights racial disparities in how healthcare resources are allocated in the United States. And this is motivated by work done by Obermeyer et al. In 2019. And so in this tutorial, we're going to consider, our task is that we're going to be building an automated system for recommending patients to this high-risk care management program. So the idea is that a patient comes into a hospital, and maybe because of their situation, we want to recommend them to a specialized care management program. We think they need more specialized treatment than just what's generally provided to individuals. And we want to recommend, we want a system to sort of take, as soon as someone's admitted to the hospital, we can say, hey, maybe this person should be recommended to this high-risk care management program or this specialized care management program. And sort of summarizing some work by the paper, Obermeyer et al., what healthcare systems are sort of more increasingly relying on algorithms to identify patients who most benefit from specialized care management programs or just the allocation of healthcare resources in general. And one convenience restriction is that in practice, if we were to actually be building this system like working with a hospital, we'd be looking at a large variety of data sets covering a wide variety of diagnoses. However, just for this tutorial, we'll be working with a publicly available clinical data set that focuses on diabetic patients from different US hospitals over a 10-year period. And so now we're going to jump into the, now we're going to actually start working with data. And so one thing I just want to check is everyone got their environment set up? Does everyone have either this running on the Colab notebook, or do you have a local environment running? No? No? Anyone having any issues? No. So for this task, we'll be working with a data set of a clinical hospital readmissions over this 10-year period from 1998 to 2008 for diabetic patients across 130 different hospitals in the United States. Each record represents a hospital admission record for a patient diagnosed with diabetes whose stay lasted between 1 to 14 days. So this patient was admitted into a hospital. They had a hospital stay lasting from 1 day to 2 weeks. And we know that one of the medical tests revealed that they had diabetes. In each patient encounter, we have information related to that patient's demographic, some medical diagnoses, diabetes medications, as well as past medical history, so number of visits they had in the preceding year, as well as payer information. How did they pay for this hospital treatment? Did they pay using public health care services such as Medicare, Medicaid? Did they pay with private insurance? And we also have information whether the patient was readmitted after release, and whether this readmission occurred within 30 days of that release. And so our task as data scientists is that we want to develop a classification model which decides whether a patient should be suggested to their primary care physician for enrollment into this specialized high-risk care management program. A positive prediction by this model will signify a recommendation for this program. So if we take in a patient's admission records and our model outputs 1, that means we recommend this patient should be admitted into this high-risk care management program. So now let's think about the task definition. What is the machine learning task we want to solve? And so a hospital readmission within 30 days can sort of be viewed as a proxy that a patient needed more assistance or care at release time. So the patient was admitted into a hospital, they received some treatment, they were released from the hospital, but then within 30 days, so within a month, they were readmitted into the hospital. And this could be for many reasons. It could be because they did not receive the right level of care the first time. It could be for a completely new reason, unrelated to why they were admitted the first time. And also because of a class imbalance, we'll be measuring our performance via balanced accuracy. So what this means is that most patients are not readmitted within 30 days, and I'll be diving deeper into the data set in a little bit. But because this data set is heavily imbalanced, we'll be working with balanced accuracy as our performance metric of interest. And another metric that we'll be considering is the selection rate of our model. So this is basically how many patients are recommended to this care management program. This is the fraction of patients, the fraction of times the model outputs this label of 1. What fraction of people are recommended to this care management program. And ideally, if we were actually building a system like this in practice, we'd also be working with healthcare professionals who would both be involved with both the design and sort of scoping out the task definition, but then also how this model is used in practice. Both how would this model, should this system be designed, but how, and once it's deployed, how should it be used by the doctors or other healthcare professionals? Yes?
When you talk about balanced accuracy, can you explain a little bit more about that? That's a foreign concept.
Yeah, so with accuracy, accuracy is basically just what's the probability, the percentage that are in true positives, true negatives, false positives, false negatives. But if your data set is really imbalanced, so say the data set is 95% zeros, then in theory you can get a model with 100% accuracy, or with 95% accuracy just by outputting 0 all the time. And so balanced accuracy, so accuracy does not work well if your data set is highly imbalanced, because you can always just always output the skewed label, the one that's more prevalent, whereas balanced accuracy sort of takes into account that the labels are skewed and sort of weights that the accuracy based on how number true positives are, how many true negatives are. Does that make sense?
Yes, thank you.
Does anyone else have any other questions at this time? No? And so some fairness considerations we want to think about when we're building such a system. Which groups are most likely to be disproportionately negative impacted by such a system? Well, if you look at the previous healthcare, literature and other healthcare resources in the healthcare space, we think that people with different races and ethnicities might be differently affected by this system. And what are the harms we expect people to experience? And this ties back to that taxonomy of harms I introduced, is that we expect people here to experience allocation harms. We have this limited healthcare, high-risk care management space in this high-risk care management program, and we're allocating space to this using the model. So if you are not allocated this opportunity, that's sort of an allocation harm. In particular, we want to pay attention to false negatives. That is, when the model does not recommend someone to this care management program, but they will be readmitted to the hospital within 30 days, because that signifies someone who really benefited from this care management program. There's like, we didn't give them the specialized care, and they were discharged from the hospital, but they had to come back within a month. And the final big question is, how do we measure those harms? And I'm going to be talking a bit more about that later on in this tutorial. And so the remainder of this tutorial will be follows. So first, we're going to sort of examine our data set and our label with an eye towards a variety of fairness issues. So, I mean, it's very common when you do a data science task, you do this exploratory data analysis. But we're going to do an exploratory data analysis, but really with an eye towards fairness-related issues. And the second part, we'll be actually training a logistic regression model, and then we'll be assessing its performance as well as its how well the model does in terms of fairness. And finally, in the last part of this tutorial, we'll be looking at 2 unfairness mitigation strategies. And so let's talk about the task definition and dataset characteristics. So 2 critical decisions when you're designing any AI system are, how do we define the machine learning task? And then what dataset do we use to train our models? And these 2 questions are often intertwined, because in a lot of machine learning and data science tasks, the dataset we use is often more so a convenience dataset. It is a dataset that is available to us, it's something we can get easily, and it's not very common in the data science machine learning space to like completely create a brand new dataset for a specific problem. If you think about like academic research or scientific research, if you have a hypothesis, you usually go out, conduct an experiment, collect data for that specific problem. Whereas in data science and machine learning, we're more likely to sort of take a publicly available data set. We have these very common benchmarks, and we just take that data set because it's conveniently available, even if it may not be the best data set for our task. And when we're exploring the data set and during our EDA, we want to think about how we want to think about the data set is we want to look at things such as sample size of our different demographic groups, in particular with attention to our different racial groups, appropriateness of our choice of labels. So this is our label readmission in 30 days. Is this really the label we should be focusing on? And finally, think about the representativeness of different features for different demographic groups. Beyond these dataset characteristics, one thing I want to think about when you talk about dataset fairness is the data set collected in a fair and ethical manner? Was the data set collected with the informed consent of the individuals represented in the data? And does it respect their privacy and autonomy? And we can document our findings about the data set systematically through this datasheet practice. And I'll touch a bit more about the datasheet practice. But by documenting our understanding of the data sets, we can communicate any concerns we have about the data set and highlight them later on downstream that might arise about any fairness-related issues that might arise during the training, evaluation, or deployment process. And so now we get to the part where we actually start running code. So first we'll load up the data set. And let's take a look at what we have. And so like I said, this is a data set pertaining to hospital admission records. And so each row represents a patient admission. We have some of their demographic information, such as their race, their gender. The age is bucketed as 3 categories, as like 30 or under, 30 to 60, 60 and above. We also have information such as how many days they spent in the hospital, number of lab procedures they had. We have information about whether they had sort of the historical patient information, so they did have emergency room visits in the past year, they have any inpatient days in the hospital last year, they have hospital outpatient days in the last year, and we also have that readmission information. We have whether they were readmitted or not, we have just readmitted in general, and then in particular, we have this readmit within 30 days. This is a Boolean variable that says, like, was the patient readmitted within the 30-day time span? And the columns in this data set are mostly Boolean and categorical data. So things like Boolean was like, did you have inpatient days? Did you have emergency room visits? And there's some other data features as well. So we have the demographic information. We have insurance information. We have hospital visits in the prior year. And we also have that readmission information, just as a summary. You can look at the full table if you want to see like all the different features in here. And we can also see the different categories for our categorical features. So we can see all the different race categories that are represented. We have 6 unique racial categories. And we also have 3 age buckets. And we also have 3 gender categories. And so now we'll just mark our categorical features. And so the first step we want to do in our exploratory data analysis is think about group sample sizes. And in the perspective of, from a fairness assessment, a key thing about a data set characteristics is sort of the sample size of groups with respect to our fairness assessments. And the thing we want to think about is that small sample sizes have really two implications for fairness assessments. One is in the actual assessment part, is that the impact of an AI system on demographic groups or other groups that we don't have a lot of data points on will be harder to assess. We'll have much more uncertainty about our estimates of our machine learning task. And then because we also have a fewer number of data points for these groups, model training will be more difficult because the model will have much more difficulty in sort of appropriately representing the joint distribution of features for that demographic group. And it may not properly capture the patterns for that smaller group, or those smaller groups may be erased and sort of underweighted by the model in order to capture a pattern that represents the majority group. So now let's examine the sample size of our groups according to race. And we can sort of normalize these frequencies above. So this gives you the raw counts. I sort of also mentioned earlier that our data set has about 10,000 data points. And so what we see is that the data set is heavily skewed towards patients labeled as Caucasian. We see about 75% of the patients who are admitted into these hospitals are labeled as Caucasian. The next largest racial group is African American, making up about 19% of the patients. And the remaining racial category groups, including unknown, compose only about 6% of the data set. And now we'll explore the data set with respect to gender. Normalize these frequencies. And we can see that the data set in our case is sort of effectively labeled as, like, gender is labeled binary. We see that about 53% or 54% are labeled as females, and 46% are patients are labeled as male. And there are only 3 patients in this data set labeled with a gender unknown and invalid. So now one thing we have to really think about, and this is a very important decision in the data processing task with respect to fairness, is how do we address these smaller group these group sizes? When data sets lack coverage of certain groups, it means that we'll not be able to reliably assess any sort of we might not be able to reliably assess any fairness-related issues. And there are 3 common interventions or data preprocessing steps we could take, and some of these could be carried out in combination. The first one is collect more data. Can we go out and collect more data for groups with fewer sample sizes? And depending on your problem, that might not be possible. If you're talking about things like crime and gun violence, for example, you can't go out and collect more data on gun violence victims, because, like, what's that mean? You're just waiting for more people to get shot. One thing you could do is sort of bucket or merge some of these smaller groups together. But and then another thing we can do is sort of drop those small groups. And so the choice of which strategies we use really affects our really has long-term implications of our modeling tasks and also of our fairness assessment. If we sort of pool different groups together, we have the risk that by pulling these different groups together, we're sort of masking the extent of harms. If we pull these small groups together and they sort of experience harms by these systems in very different ways, we're sort of masking that because we're sort of saying that you're all grouped together as this one group, even though you are really 2 different sets of people. And we also generally caution against dropping smaller groups because this leads to this representational harm of erasure. If you remove them from the data set, such as removing gender non-binary or gender non-conforming individuals from a data set, you learn this risk of erasing those people from the data set and from the model. If any groups are merged or dropped, these decisions should be annotated or explained in either a data sheet or some other documentation. In our case, we'll be merging the 3 smallest racial groups, Asian, Hispanic, and other. And this is sort of based on the original paper that uses this data set, Strack et al. But we'll also retain the original groups for accelerated assessment. And then we'll also drop the gender group unknown and valid because the sample size is so small. We only have 3 data points for this gender group that no meaningful fairness assessment is possible. And so as a brief exercise, if you just want to actually like practice running some code, you just could play around with sort of doing what we did above, but looking at the distribution of the age category. I have the answers down below if you don't actually want to do this, but it's something I would recommend, just looking at the age categories and start thinking about like what potential fairness-related harms could be introduced at the age level. So we've talked about a bit about race and gender, but what types of representational harms could be introduced by imbalances in the racial categories, the age category? Give you one. Yes. So that's one thing you mentioned. So discrimination against older people, it could be discrimination against younger people. It also depends on like what is the representation of people in this data set. So it could be if we have younger people underrepresented in the data set, we could be discriminating against younger individuals. And so once we do this exploration of our age feature, we actually see that most individuals in our data set, most patients admitted to the hospital belong to this category of over 60 years old. And well, for the sake of this tutorial, we'll not be doing any sort of assessments related to age-based fairness-related harms. I do think it would be worthwhile that we do document this age imbalance in our data set, in our data sheet practice for further assessment, so that someone who is interested in thinking about like fairness-related harms on related to different age categories would be able to sort of have this artifact here and say like, oh, we believe this might be an issue. Here's a nice starting point for us. And so now let's talk about examining the choice of labels. And I think this is a very interesting one because this is not talked a lot about in the common data science exploratory data analysis process. We sort of talk about like what is the distribution of that label, but we don't really talk about like, does our label actually represent the thing we want it to, we care about? Is like, are we optimizing for the right thing? Or are we just meaningly optimizing for this value because it's available to us? And so in this session, we'll be sort of exploring this question of whether our choice of label, readmission within 30 days, sort of aligns with our goal, which is to identify patients that would most benefit from this care management program. As stated earlier, this readmission within 30 days is sort of this heuristic or proxy that we'll be using for identifying patients who would most benefit from this care. But we do recognize that as a proxy, it has some limitations. Yes? So we don't have that, and so this is actually what this section is about, is like, we have this proxy, and we don't want like perfect to be the enemy of the good, but we want to ask ourselves, is this label even like remotely aligned with what we care about? And so I think there's many cases where data science projects really go wrong because you optimize for a label that has nothing that relates to nothing related to like the main business objective. And so the section here will be sort of asking ourselves like, we don't think this is a perfect label. Like in a perfect world, we would have a label that says like how much a patient would benefit from such a care management program, but this is what the best thing we have, and I think we're asking ourselves, is this really good enough? Is like, do we have something that's like close to what we want, but not perfect, and thus, is this something we want to continue doing our data analysis with? And so the idea is like, is this worth moving forward with? Like, do we think that this label readmission within 30 days is somewhat related to that concept we care about? Like, who would benefit from this care management program? Does that make sense? Yeah. And so this is actually what this section is about, is we'll be introducing this idea of constructability from the quantitative social sciences in order to sort of assess whether our label is actually a good choice of labels. And the idea of this is that, do you have a question or?
Yeah, I do.
Yeah.
Are we assuming that this high-risk program already exists and has been applied to some of the people in the data set?
No, so it's like we're sort of creating a new program, and we sort of want to roll and sort of figure out like who would benefit from such a care management program. And so the idea of constructability from the quantitative social sciences falls from the idea that like a lot of things that social scientists care about are sort of abstract ideas. If I ask you like, what is the health of a democracy? That's this very abstract ideas. Well, then social scientists have to come up with experiments and measurements to sort of measure that. And they can do this in different ways. They could look at things like, what percentage people vote in elections, how much of like journalism is independently owned and not like run by the state. You can use things like that to sort of measure this idea of health of democracy. And we're going to be taking that idea and applying it to our task. And so this paper, Jacob and Wallach's 2021, introduces this idea of measurement modeling, is particularly with an eye towards fairness. And the goal of measurement modeling is to describe the relationship between what we care about and what we can measure. And the thing we care about is often called a construct. And the thing we observe is often referred to our measurement. And so in our case, that abstract construct we care about is who would receive the greatest benefit from this care management program. And the thing we can measure is readmission within 30 days in the absence of such a program. So we have this abstract thing we care about, we have something we can measure, and the question is like, how closely are these two related to each other? And in our case, our measurement sort of corresponds with our classification level. And in the quantitative social science literature, this is often called operationalization of a construct. So we sort of have this abstract idea, we sort of operationalize it by sort of saying, here's this concrete thing we can measure. And when we do that, we sort of make certain assumptions. And in this case, we're making this big assumption that the people who would receive the greatest benefit from our care management program would go to the patients who are most likely to be readmitted within 30 days. And so we want to sort of test whether that is true. And how can we test whether this assumption applies? And so in this paper, Jacob and Wallace, they sort of talked a bunch of different ways you can sort of test or establish construct validity. And so this is looking at things like, does our measurements look plausible? Do they correlate with measurements of the same construct? So is our label sort of correlated with things we expect it to be correlated with? And are these measurements predictive of measurements of other observable properties? And so if you read the full paper, they talk about different aspects of construct validity. In particular, we're going to focus on one aspect, which is predictive validity, which refers to the extent that measurements obtained from our measurement model are predictive of measurements that are closely related. So if we think we care about is sort of great patient care, and we're measuring that through who's readmitted within 30 days, is this label correlated with other things we expect to be correlated with who would benefit most from patient care? Does that make sense? And so with predictive validity, we want to show that our measurement, readmit within 30 days, is correlated with patient characteristics that would sort of, we believe to be related with our construct of benefiting from care management program. And so one such characteristic is sort of general patient health history, where we expect that patients who are historically less healthy will be the ones who are more likely to benefit from this care management program. And so while it does not contain full healthcare records that would allow us to like holistically measure general patient health, we do have two relevant features: had emergency days and had inpatient days, which indicates whether the patient spent any days in the past year in the emergency room, or did they spend any days in the hospital but not in the emergency room within the previous year. And so to establish our predictive validity, we want to show that our measurement, readmit within 30 days, is predictive of these two observable characteristics. So the idea is that can we use our label, readmit within 30 days, to sort of make some prediction about whether the patient had emergency room visits in the previous year, or did they have hospital visits in the previous year? And so one thing we can do to do that is sort of check the rate at which patients were, who were readmitted within 30 days, had emergency room visits in the past year. And so if you look at this graph, and what this means is, we start at the x-axis, yes?
Sorry, are they readmitted for the same reason as their diabetes, or for any reason?
For any reason, and this is part of the reason this is a proxy. So they could be, they're admitted to the hospital for a diabetic-related reason, but let's say in like 2 weeks they got into a car accident or they're readmitted to the hospital. So they were readmitted within 30 days, but it's for a completely unrelated reason. And that's part of this reason that this label may not be perfect for what we care about.
Why are we even considering the label?
So, I mean, in most cases, we're probably never going to have a perfect label, and this is sort of the convenience that, like, this is the best thing we have, and I think it's important to understand, like, even if we're sort of using the best thing we have, we understand the limitations of that, and I think that's a part that's sort of glossed over when we talk about data science context, is sort of just assume that your label is perfect, even though it may not perfectly capture the thing you really care about. Any other questions? And so what this graph shows is that readmit within 30 days is that patients who were readmitted within 30 days are much more likely to have emergency room visits in the previous year. So this idea that patients who were readmitted within 30 days are more likely to have hospital emergency room visits. And so this is sort of a good thing, because it sort of says that, like, hey, our label, which we believe corresponds to patient health, is correlated with this feature that is actually correlated with patient health. And we see a similar pattern when we compare readmit within 30 days to had inpatient days. So once again, we see that patients who were readmitted within 30 days had a much higher probability of having an inpatient day in the previous year. So patients who were readmitted within 30 days were more likely to have hospital visits in the preceding year. And now let's take a look at whether this predictiveness is similar across different racial groups. And so what we see is that patients in the unknown, so we see here, so we have our x-axis on whether the patient was readmitted, and we have whether they had emergency room visits. And what we see is that patients who have this racial group unknown had substantially lower number of emergency room visits in the prior year, regardless of whether they had, whether they were readmitted within 30 days. But this readmission is still positively correlated with had emergency room visits. But but also note that we have a larger error bar just because of the smaller sample size. We also see that that the group labeled as African Americans had a higher room of emergency room visit. The group labeled as African Americans had a higher rate of emergency room visits compared to other racial groups. But overall, the groups Caucasian, African American, and other follow similar dependency patterns. We also see a similar pattern when readmit 30 days is used to predict whether a patient had inpatient days. And so again, for the unknown, the group labeled as unknown, we see that the rate of our non-emergency room hospital visits in the previous year is lower for all compared to other groups. So here we see that it's much lower compared to the other racial groups in both readmit 30 days being 0 and readmit 30 days in 1. But in both cases, in all cases, we really see that our readmission within 30 days is predictive of our two measurements of general patient health. And so this helps us establish that predictive validity that our choice of label, readmission within 30 days, is actually something we think might be worthwhile modeling. We believe it is correlated with something that corresponds to lower general patient health, and that lower general patient health would be some people who would benefit from this care management program. So that gives us some evidence that, hey, this is a worthwhile label that we should be using, even if though it may not be perfect for reasons that people have mentioned earlier. And so now, as a quick exercise, you could also look to establish predictive validity with respect to gender and race. So looking at that inpatient days and see how it's broken down by race and broken down by gender and also broken down by age. And you can ask yourself, do you see any differences? And if you do, can you form a hypothesis about why? So I'll give you like 1 to 2 minutes so you can run this and look at the results and sort of think about like why do you have those results? So if we do run this, we see that when broken down by gender, we're not really seeing any major significant differences between male and female, and sort of had the inpatient days regarding to whether you were readmitted within 30 days or not. But we still do see this trend of readmit 30 days being highly correlated with inpatient days, but we don't see really any differences by gender that would make us suspicious of any gender-related, fairness-related harms. When we do break it down by age, we do see that younger patients people who are 30 years and younger, they're more likely to have higher inpatient days if they're readmitted within 30 days. So this gives us some evidence that, hey, that there might be some relationship between our label had readmitted within 30 days and sort of had inpatient days. And if you think about this hypothesis, it kind of makes sense that like if a younger individual had a hospital visit in the previous year, that might be more signs that that person has like health problems or health issues, and they would benefit from such a, or maybe they have like ongoing health issues, and thus they would benefit from such a care management program. Does that make sense? Yeah. And finally, the last thing we want to talk about is sort of label imbalance. And so now we've established, the validity of our label, that, hey, we should be using this label of within 30 days. We can now check the frequency of this label in our data set. And the frequency of different labels is important. In general classification sets, for many reasons, some classification algorithms and performance measures may not work well with data sets with extreme class imbalance. Accuracy, for example, does not work well with extreme class imbalance. And in a binary classification setting, our ability to sort of estimate the errors of our model is really driven by the size of the smaller of the two classes. So the smaller the sample, the larger we have uncertainty or error bars in our model. And finally, label imbalances may exacerbate problems due to that smaller group sizes in fairness assessments. And so if we have very imbalanced labels, we also have very imbalanced demographic groups, then the intersection of those two imbalanced labels, imbalanced demographic groups will lead to a lot of issues later on. So now let's see how many samples of our data are labeled as positive, how many labels as negative. And as we can see, the target label is heavily skewed towards patients not being readmitted within 30 days. In the context of our data set, only 11% of patients were readmitted within 30 days. And since there are fewer positive examples in our data set, we expect there to be much higher uncertainty or error bars in our estimate of the false negative rate compared to the false positive rate. What this means is that we expect there will be larger differences between the training false negative rate and the testing false negative rate, even if there is no overfitting, simply just because of the smaller sample sizes. And as a result, our target metric is balanced error rate, which is the average of the false positive rate and the false negative rate. This metric is much more robust to different frequencies of positive and negative. However, because half the metric is contributed by the false negative rate, we expect the uncertainty in the balanced errors to behave similar to those of the false negative rate. And so now we can look at the different labels or distribution of our labels by race. And what we see is that the 30-day readmission rate is similar across African Americans and for Caucasians. So both for this label is about like 10.5, 11%. And it appears to be a bit smaller for the other and unknown group. And this is consistent with our overall lower rate of hospital visits in the previous year. And one thing to keep in mind is that because of our smaller sample sizes for this other and unknown group, we also have much more uncertainty around these estimates. And finally, one thing we want to think about is sort of proxies for sensitive features. And so in this last section, we'll sort of be exploring these proxies for sensitive feature for our sensitive feature race. And while in this tutorial, we sort of examine fairness issues through the impacts of machine learning models. There are sort of other concepts of fairness that sort of are focused on how machine learning models might be using information contained in sensitive features, and which use of these features are sort of justified. And in this, more pragmatically, what this means is that in certain scenarios, uses of certain sensitive features may be illegal, or it could be legal depending on the context. And another reason we want to think about proxies is they might help us explain the differences we see in our impact of our different groups, even when our model does not have access to our sensitive feature of race directly. So even if our model is not using race in its predictive modeling, if it's using a proxy, we might see disparities according to that race feature just because its model is using a proxy. And so in this brief section, we'll sort of briefly talk about how we could identify certain proxies. And so key thing about proxies is I think they're very heavily dependent on our understanding of the context of our problem. And so in the United States, for example, Medicare and Medicaid are two joint federal and state programs to help qualified individuals pay for healthcare expenses. Medicare is available to people above the age of 65 and younger people with severe illnesses, and Medicaid is available to all people under the age of 65 whose adjusted income falls below the federal poverty line. So let's first explore the relationship between people who pay with Medicaid and our demographic feature race. Because Medicaid is available to low-income individuals and socioeconomic status is correlated with race in the United States, we expected to see some relationship between race and paying with Medicaid. And so if we look at this, we do see that there is some relationship with paying there is some relationship between paying with Medicaid and the patient's race. In particular, Caucasian patients are least likely to pay with Medicaid compared to other groups. And so now if we believe that if paying with Medicaid is a proxy for socioeconomic status, then we find the patterns that sort of align with our understanding of wealth and race in the United States. And if we were to use this feature, paying with Medicaid, in our modeling test, we have a feature that is now somewhat correlated or a proxy for race. And so now, as a brief exercise, we can sort of look at the relationship between paying with Medicare and other demographic features. And in this section, you could just run these 3 plots, or you can sort of look at any other relationship you care to look at. And so in particular with Medicare, like I said, because Medicare is available to people above 65 and above, we expect this feature to sort of be a proxy for age, right? People who are more likely to be older are more likely to be paying with Medicaid or Medicare. And if we do run these plots, we do see that that is very much the case, that people who are above the age of 60 are much more likely to be paying with Medicare. But we don't see strong evidence for Medicare payment to be sort of a proxy for other features as well. One thing to mention about this is that it looks like there's a difference, but I think also just look at the scale of this plot. It's from 0.03 to 0.33. So it looks like there's a significant difference, but the scale of it is very small. And finally, let's wrap up this data exploration section by talking about data sheets. So the data sheets practice was sort of proposed by Timnit Gebru and other researchers at Microsoft Research back in 2018. And what a data sheet is a document that sort of describes the motivation behind a dataset creation, the dataset composition, collection process, and any recommendations on how the dataset should be used or other characteristics that should be that's worth documenting. And in the words of the authors, the goal is to better facilitate communication between dataset creators and dataset consumers, and encourage the machine learning community to prioritize transparency and accountability. And so I'm not going to go through how to create fill out an entire data sheet because it's 65 questions. But the main idea is that there are different sections of this, and we want to maybe think about which ones are worth filling out. So things like for what purpose was the data set created? Was there a specific task in mind? Did it fill a particular gap? And you can see the authors say, yes, there was a gap that needed to be understood in the hospital, healthcare management space and healthcare modeling space for diabetic patients. Documenting what does each instance in the data set represent, and that each data instance represents a hospital admission. And think about missing information, but also identifying subpopulations by different demographic groups. So here we can sort of identify our subpopulations by gender, by age, and by race, and then also documenting some pre-processing that we did, such as the binning of the racial groups or the dropping of that gender unknown invalid, but also other pre-processing tasks as well. So at this time, we've sort of going through the data set, and we'll take a 5-10 minute break. So get up, stretch your legs, get some water, and then when we get back, we'll actually dive into how can we now train an initial machine learning model, and how can we sort of assess it for fairness-related harms. So it is actually not 4:30. Wait, is it 4:30? It is 2:30. It's 2:30, so let's say be back here by 2:35, 2:40, and then we can jump into the next section. Okay, welcome back, everyone. So in the first hour of the tutorial, we sort of talked through, give an overview of what fairness in AI and machine learning is, and also talked through our data set and our sort of tasks that we want to solve for this sake of this tutorial. And we went through the data set, we looked at it for a variety of fairness-related issues, and we decided, hey, we think this label is not perfect, but it's good enough to keep going, but we also do think that there will be some fairness-related issues downstream. And so in this next section, we'll be now training an initial model, and we'll also be using the Fairlearn library to sort of assess and measure the fairness-related harms in that machine learning model. And so our goal is that we want to train a classification model to predict this target variable reemission within 30 days, while optimizing for that balanced accuracy metric. And so key question we want to ask ourselves is, what kind of model do we want to train? Do we want to do a deep neural network? Do we want to do a random forest? Or a logistic regression? And there are plenty of considerations you should think about when you decide what type of model you should use. And we're going to highlight two. One is interpretability. Interpretability is highly linked to this idea of this concept of fairness. If you look at the academic research, AI fairness, algorithmic fairness is very related to model explainability, model transparency. They're at the same conference of fact. This is the general idea, like fairness, accountability, transparency. And there are several reasons why having interpretability is very important. One, allows our model to be sort of open to stakeholder scrutiny. It allows for domain experts who are not necessarily data scientists to come in and sort of analyze our model and maybe identify some fairness-related issues that the data scientists may not have knowledge about. It also provides a path for recourse, and I think this is the most important part. And by recourse, I mean, really when you have these machine learning models, it's sort of a good outcome and a bad outcome. You get a job, you don't get a job. You get a credit loan, you don't get a credit loan. There's a good outcome and a bad outcome, and recourse is sort of asking themselves, what do you need to do to get that good outcome? How do you go from not credit loan to credit loan? How do you go from no job to job? Like, what changes do you need to make? And interpretability gives us a pathway to do this. By sort of understanding how the model is working and what the model used to make that decision, we have a way to sort of provide that user or that applicant some guidance of what they need to do better next time. And finally, interpretability allows for a sort of face validity check or sort of a sniff test to sort of verify to get the expert's opinion that sort of like the model makes sense, that the model is sort of optimizing or focusing on the features that we think are really relevant. I think there's plenty of stories about machine learning models getting good accuracy, but it turns out they're optimizing for the wrong thing. So famous example is that there was a computer vision system looking at chest x-rays, and really what the model was picking up on is whether the patient was standing up or sitting down, because that's very correlated with whether this patient had some disease or not. And so explainability would also see like, hey, is the model actually picking up on some spurious correlation that's very correlated with their label in the training data set? Another thing we also want to think about is sort of model expressiveness. How well can our model sort of distinguish between the positive class and negative class? And how well can it do that given the size of a data set? There are some machine learning models that really work well when you have lots of data points, but don't work so great when you have very few data points. And in terms of fairness, we also want to think about, can the model generalize well across all the different demographic groups? Or will it sort of we'll need to do sort of take some trade-offs of performance against smaller demographic groups? There are also other considerations you might want to think about, such as like training time. So how long does it take to train that model? Because that affects how often you can really iterate on it. If a model takes weeks to train, you really can't iterate on it often. You also might want to think about how familiar you are with the model, because that could sort of that sort of affects your ability to sort of debug the model. If you're working with a model that you're not really familiar with, you don't know how to tune its hyperparameters, or you might not be sure how to debug the model. And finally, a topic that's becoming very increasingly discussed in the responsible AI space is sort of like, what is the climate impact of a machine learning model? What is the carbon footprint? And so this is both thinking about this idea of like, how does the training model process sort of affect the Earth's climate directly? But also we don't want to normalize normalize doing unnecessarily heavy workloads. Like, we don't want people just to like spin up a couple of cloud instances and train some neural network on GPU when they don't have to. We would rather them not like waste those unnecessary workloads and use a simpler model if necessary or possible. And so at this choice, we're going to go with using a logistic regression model. And so our reasoning is that as follows. In terms of interpretability, a logistic regression model works really well over when given a small number of variables, such as our example in our case. Interpretability comes very easily. It's very easy for us to understand like, what is the relationship between our features and the outcome. because linear logistic regressions have sort of like that linear dependencies. So we have interpretability. And now one concern with logistic regression might be like, well, what is the model expressiveness? That because these models are a bit simpler, they might not be able to learn the pattern well. But if you look at the previous work by the original authors of this dataset, Strack and et al., they used a logistic regression, and they were able to predict readmission rates relatively well, and they found that also that a slightly more expressive model doesn't really, may not be, the benefits of a more expressive model are not really that significant. And so with that said, like, we like interpretability. We're not too concerned about the limitations of model expressiveness. And so we're going to go forward with a logistic regression. And so now let's prepare our training and test data set. So our target variable is readmission within 30 days. We'll be pulling out our sensitive feature as race. And so just denote them here. And now we'll create our y column. So this is our target variable, along with this sensitive feature column, which is going to be our race column. We will also create our training data set, X, and also dump the race features from that data set, along with our target labels, so all the re-emitted ones. And you can see what our data set looks like here. So here we have all the features. So we have time in the hospital. We have the procedures. We have admission information. We also have a bunch of dummies for medical tests. But we no longer have this demographic information. And we also don't have our labels. And now we're going to split our data set into a training test portion. And so usually when you do this in a standard data science task, you use the train data set to sort of train the model, use the test model to sort of evaluate the model for performance. But we'll also be using the testing data set, in our case, for our fairness assessment. So the testing data set will be used for both evaluating the model's performance in terms of just predictive accuracy, but also be used for our fairness assessment, sort of like how well does our model do with regards to our different racial demographic groups. So just setting a seed. And here we're going to create our X train, X test, Y train, Y test, but also our sensitive feature sort of as the training and sensitive testing separations. And so our performance metric is going to be balanced accuracy. So the purposes of training, but not evaluation, we'll be resampling the data set such that it has the same number of positive and negative examples. And this means we can use estimators that directly optimize standard accuracy. Although there are many estimators in scikit-learn that allow us to use important weights, we're not going to do that right now because the scikit-learn important weights don't play well with Fairlearn inner workings yet. We have a version release coming out soon. We'll hopefully fix that issue. And so how we're going to resample this data set is that we're going to downsample the number of negative examples. So we're going to create a data set by downsampling the number of negative examples such that there is an equal number of positive and negatively labeled data points in the data set. So now we've created our training, our resampled training data sets. So X train balanced, Y train balanced, and A train balanced. So these are the training data sets, but they're resampled or downsampled to be more even. And so now let's create some descriptive statistics, and we're going to sort of save these visualizations. And so these will be used later on when we create our model card, but we're just going to look at these now. And we see, related to race, here's the distribution of race within our training data. So we see that, once again, that the sensitive attribute race is heavily skewed towards Caucasian in the training data set, but it sort of follows the distribution we saw earlier above when looking at the entire data set. When looking at the distribution of the label in the training data set, yes? So in practice, you could use SMOTE or scikit-learn imbalance in order to do some other strategy. I chose not to do that just for the convenience of a tutorial. Like, I don't want to add an additional dependency if I don't have to. But you can use SMOTE or some other imbalanced data set imbalance strategy for this. I guess also the part of the reason is that, like, just by making the data set slightly smaller, it makes things faster to run for the rest of the tutorial, which is, kind of nice, so they're not just sitting here for 5 minutes waiting for code to run later on, which will happen. I will give that disclaimer that it's going to happen, where later parts of the code will take a while to run. So here we see that our data set is now downsampled. The training data set is now downsampled to be more balanced. But when you look at the distribution of the test data set, we see that our sensitive feature is now has the same distribution as the testing data set, or relatively the same. But when we look at the target label, that we still see that imbalance that we saw earlier of that like 90-10 split in the test data set. And so now we're going to train our model. So we're going to train our logistic regression and sort of save as predictions on the test data set for analysis. And so we'll be using the scikit-learn API. We'll use a pipeline to sort of pre-process the numeric features using standard scalar, and then pass it into a logistic regression. We fit the model to the training data and the testing, training labels. And we get our model predictions on the test data set. And so now, as like a quick heuristic, we can sort of check our model performance on the test data set. So one thing we can look at is the ROC curve, and we can also look at the balanced accuracy score. And so what we see is that our model is doing better than like average. So we have like 60% accuracy and 63% AUC. So it's like far from perfect or far from ideal, but it's a bit better than like a random coin flip, for example. And one thing we might also do in terms of interpretability is to sort of look at the coefficients. It's just to make sure that they sort of make sense. And so while this is subjective, I think this step is important because this is a place where like domain experts can come in and sort of check like what are the features that your model is most focusing on to make sure like these sort of make sense with their expertise and their intuition. And one thing to keep in mind is that in logistic regression, that like these coefficients are sort of, the feature importance of coefficients is like a proxy, but these interpreting it sort of, these coefficients as features importance, can be sort of misleading if the features are highly correlated. So we look at the features that it's most focusing on, and we see that like if a patient had inpatient days or had emergency days, that's most correlated with the patient being readmitted within 30 days. So that kind of makes sense, both with the analysis we did above, but sort of our general concept that like having inpatient days or having emergency room visits is correlated with poor patient health and thus be more likely to be readmitted within 30 days and thus benefiting from this care management program. So we sort of passed that initial validation check. So we've now trained our initial model. Let's get into the main part of this, which is how do we do a fairness assessment? And so the goal of any fairness assessment is sort of to answer this question of which group may be disproportionately negatively impacted by a machine learning model or AI system, and in what ways. And how we're going to do this assessment is sort of broken down into 4 steps. First, we're going to identify the harms that the system can produce. And so in identifying harms, we want to go back and reuse that taxonomy we introduced it above. And so, for example, in a system screening for job applications, qualified patients that are automatically rejected sort of experience this allocation harm. On the other hand, if you have a speech-to-text transcription system, higher word error rates may constitute a harm in terms of quality of service. Like no one's being allocated a service or being withheld opportunities from this speech-to-text transcription service. But if it's producing a higher word error rate for me compared to you, that I'm experiencing sort of a quality of service harm. It's not working as well for me as well for other people. And tying this back to our healthcare scenario, the patients that would most benefit from this care management program, but are not recommended for this, experience this allocation harm. In particular, in the context of this classification task, it corresponds to our false negative. So these are the people who would benefit from this care management program, but they are not recommended to this program. They experience this allocation harm because they are withheld this opportunity to participate in this program. And next, we want to identify who might be harmed. So in most applications, we really think about demographic groups, such as historically marginalized groups, often based on gender, race, ethnicity, disability status. But we also might want to think about groups that are specific or particular to a given application. So for example, in speech-to-text transcription, groups based on regional dialect or being a native speaker of that language, how do you compare their word error rate to people who are not native speakers of that language? Do non-native speakers have a higher word error rate compared to native speakers? And that's correlated with demographic features, but it's not entirely related to one. And it's also worth thinking about group intersections. So thinking about, in addition to just like one specific demographic group related to gender or demographic group related to race, we want to think about the intersection of these groups, such as Black women or Latinx non-binary individuals. And so in our healthcare scenario, which group do we expect to be negatively harmed or impacted by the system? We believe those are groups defined by race. So now we've talked about what types of harm we anticipate and who do we think is going to be harmed by our system. So next, let's talk about how do we quantify these harms. And I think this is the key part of a fairness assessment is that when you talk about what metrics you want to use, and I think this is the common question that people ask is like, when we talk about fairness, it's like, which metrics do I use? There's like so many of them. There's like 20, 30 metrics. How do I know which ones to use? And for the most part, most of those metrics are vanity metrics, and they're not relevant to your application. You really should be able to tie your metric, or your fairness metric of choice, to some specific harm that someone is experiencing. If it's not related to a harm, it may not be worth caring about, because really, the reason we care about AI fairness is that people are being harmed. And if no one is really being harmed, is it really something we should be worried about? And so in this so define the metrics. So we're going to define our metrics that sort of quantify harms or benefits. And so in that job screening scenario, we want to quantify the number of candidates who are classified as negative, so they're not recommended for a job, but whose true label is positive, that they are qualified. In that case, that would correspond to that false negative rate, and that's the sort of fraction of qualified patients who are screened out. In a speech-to-text scenario, the harm can sort of be measured by this word error rate, so how number of mistakes in the transcription divided by the overall number of words. So like how often does the service sort of mistranscribe the word you were saying. In our healthcare scenario, we're going to be thinking about two metrics for quantifying harms and benefits. So one is the false negative rate, and this is what we've talked about before. So this is the fraction of patients that are readmitted within 30 days, but are not recommended to this healthcare, this high-risk care management program. So this is the fraction of patients who would benefit from this program, but are not recommended to it. And this represents that allocation harm we talked about as above. But we also want to think about the selection rate. This is the fraction of patients that are recommended to this care management program. So this is the percentage time the model just outputs that label 1. The fraction of people who are recommended to this care management program, even if they are not, regardless of whether they're readmitted within 30 days. And the reason we want to think about this is it sort of quantifies a benefit. Like being recommended to this care management program, even if you don't need it, is sort of a benefit. And we hear the idea is that like we don't want to over-allocate this program to people of certain demographic groups and under-allocated to other people of demographic groups, regardless of whether they need it or not. And there are other additions we want to think about multiple metrics when we talk about our fairness-related harms, is that we will sort of want to understand like both the harms and benefits. And it also gives us extra robustness. By focusing on multiple metrics, we sort of get a better view of sort of how our model is being deployed and the ways that our model is interacting with the real world. By focusing on like a particular one metric and sort of just optimizing for that, you can get a very narrow idea of fairness. And you might be focusing on something too closely, and you might miss the forest for the trees. By looking at multiple metrics, you can sort of build a more robust picture of what's going on in the real world. And finally, after we define our metrics, we can sort of define our harms across different groups. And so the way we can do this is through disaggregated metrics, which is metrics trained on evaluated on different slices of the data. In particular, the different slices correspond to our demographic group of race here. And so we do this by evaluating the errors on each slice of data that corresponds to the demographic groups we identified in the previous step. If we see that some groups are experiencing much higher error rates than others, we might flag this as a potential for fairness-related harm. And to do this, we might summarize the disparities in the word error rates or other metrics. We might want to report quantities such as the difference in the error rates or the ratio between the metrics between the best and worst slice. In settings where the goal is to guarantee a certain minimum level of quality, we might want to report the worst case performance. So if you're deploying like a face detection system or a speech-to-text transcription system, it might be worth recording what is the worst performance across all demographic groups and saying that, hey, before we deploy this system in practice, we have to ensure we're getting at least 80% accuracy for all demographic groups. And so for example, when comparing the false negative rate across different groups by race, we might summarize our finding by this. And so here we have on each row, we sort of have the different demographic group, racial group, and we have the false negative rate for that group. And then we can also show the largest difference, so 0.24, which is the difference between the largest false negative rate and the smallest false negative rate, so that 0.67 minus 0.43. The ratio, which is sort of the ratio of the smallest group to the largest one, so 0.43 divided by 0.67. But then also reporting that maximum false negative rate, which is a worst case false negative rate, which is 0.67 for the unknown demographic group. So how do we do an assessment like this? That's when we start, And this is where Fairlearn comes into play. And so within Fairlearn, we provide a data structure called the metric frame that makes it easy to evaluate these disaggregated metrics. And we'll be using this metric frame in order to sort of assess the performance of our logistic regression that we trained earlier for potential fairness-related issues. And so how does the metric frame work? Well, it sort of, if you've used scikit-learn or pandas, the API will seem very familiar to you. So what we do is we pass in our metric. In this case, it will be the false negative rate. We pass in our ground truth, which is the y true. In this case, this will be the labels of the testing data set, y test. We pass in our model predictions, y pred. And we also pass in our sensitive features, which is the race. And then we can call this by group attribute. And we can get a disaggregated evaluation of our model by our feature, false negative rate. So here's sort of the false negative rates for our different racial categories. And here we can see like the 0.43 for African American, 0.44 for Caucasian, 0.52 for other, and 0.67 for unknown. In addition, like I said, it would be worth reporting the differences, the ratio, or the maximum across group. And the metric frame makes it easy to do that with simple function calls in order to report difference, ratio, or group max. And so here we can report the maximal the difference between the smallest and smallest. We can report that ratio, and we can report that maximum false negative rate achieved. One nice thing about the metric frame is that you could actually pass in multiple metrics to it. So rather than passing in just one singular metric, what you do is you pass in a dictionary of metrics. So mapping a metric name to some function, and this function is sort of like a metric in the scikit-learn API. So it takes in a function that takes in a y true and a y pred. And you pass these in as a dictionary. You pass in the ground truth, you pass in the predictions, you pass in our sensitive features. And when we call group by group this time, we can see the disaggregation of all three metrics that we looked at, the selection rate, the false negative rate, and the balanced accuracy score, disaggregated by our racial categories. And we can also report differences by our different features here. And now one nice thing about metric frame is that because it's built on top of the Pandas API, we can take advantage of Pandas' like native plotting capabilities in order to visualize some of these metrics as well. So we can call the metric frame by group, plot, and then sort of visualize our model's performances across each of these different features broken down by the different demographic groups. And we see something like this. And so what you might notice here is that it appears that the group unknown is selected for this care management program less often compared to other groups. And this is reflected by the selection rate. So the selection rate represents how often do we recommend people of that group for this care management program. And you can see here that the rate of selection for the unknown racial group is lower than the other three racial groups. On the other hand, we also see that the false negative rate for the unknown racial group is much higher compared to the false negative rates for the other three groups. And we saw that numerically above, where we saw that the false negative rate for this group is 0.67, and the other ones are 0.42, 0.43, and 0.52. And we also see that the balanced accuracy is lower for this group, but it also doesn't seem to be like dramatically lower or noticeably lower compared to the other three racial groups. And so the key thing about this is we observed this disparity in the model's performance, broken down by the racial feature, even though we did not include race in our model predictions. And so there's a variety of reasons why such disparities might occur. It might be due to representational issues, not just enough instances per group, or because the feature distribution itself is different across groups. And in practice in the real world applications often have multiple kinds of issues about why such sort of performance disparities occur. And so here we see that I guess to recap what I just said. So with the false negative rate being higher for this unknown for this unknown group, and the selection rate being much lower, is that these people in the unknown racial group are more likely to benefit from this care management program, but they're also less likely to be recommended to this care management program. And so in this case, our model is producing an allocation harm towards these people. And so now, we have a fun exercise, and in your notebooks, if you're using the student version, there'll be opportunities for you to sort of play around and sort of try to train your own fairness unaware model and run the metric frame on this. And so in this section, I'll give you about 15, 20 minutes because this is like the first real exercise. You could train your own fairness unaware model. So you could train another logistic regression. You could train a random forest. You could use you can use the histogram gradient boosting classifier, so a boosted tree, or train any other model you want on the data set, get the model's performance, and then use the metric frame in order to evaluate it for different fairness metrics. In particular, I recommend try to use metrics that are different from the ones we use above. So rather than thinking about false negative rate, balanced accuracy, and selection rate, try these different metrics such as count, which is the number of data points belonging to a sensitive feature, the false positive rate, or the recall score. And so if you're using this, like I said, if you're using the student notebooks, you should see something like this where there are cells, and they have sort of like fill in the blank here. So these sort of give you some guidance, but allows you to give an opportunity to explore and sort of play around with the metric frame APIs, try to create some visualizations, and see what you can do with the metric frame and sort of evaluate the models for different fairness-related issues. Is there any questions about what you're supposed to be doing at this time? No? Great.
I noticed that it's easy to copy intersectionality by listing sensitive features as multiple.
Yes.
A list of them, which has an interesting effect, and other people might enjoy looking at that. For example, this may simply have to do with the relatively small sample of the intersectional groups, but we have like a, actually, I'm sort of misreading it. But, no, that's correct. Like there's a very bad false negative rate for African Americans under 30, while it's less extreme for other age groups.
Yes.
And so you may find those kind of intersectional effects in
Yes.
the bias that's detected.
Yes. Yeah, actually, that brings up a good point. And so, like you said, like one thing with a fair metric frame makes it easy to do is actually test the intersectionality of different groups. And so rather than just looking at race again, you can now look at the intersection of race. You can look at the intersection of race and gender. You can look at the intersection of race and age and see what kind of results you get with that. And look how the model, the metric frame performance is sort of changed when you do that. And so, like I said, it would take about 5, 10, 15 minutes. And so it is actually 3:10 right now. And so I'll say 3:25, we'll come back and continue going. How's that sound to everyone? I'll be walking around, and so if anyone has any questions or any comments, I can answer them at this time. Also, feel free to use this time to take a break if you need it. Like I said, we'll come back at like 3:25, and so if you need to go up, get coffee, stretch, use the restroom, feel free to do that at this time as well. Yeah.
Expect F1 score to.
Yeah, so any metric available in F1 score, you might want to think about like if the metric is imported above. So actually, you scroll up. Yeah, just put an import statement if it's because like for these three, I've already actually did the import for you. So if you want to do something like F1 score, you have to. Yeah. And also one thing to keep in mind is like if you can do this with like sort of like metrics that sort of take in like a probability distribution. So like if you have like y true being like ones and zeros, but y pred being like probabilities, you can do that with metric frame, but you just have to define it a bit differently when you do this exercise part.
Cool. Okay.
Yeah. Yes.
I was listening to you, and so I'm working through some of these. But here's a question.
Yeah.
For example, in the section where you talked about, using logistic regression to model those, that statement, the feature importance in the interpretation can be misleading. That's critical because we make the fundamental assumption that the features are conditionally independent,
Yeah.
right? And that's a normal assumption. But do you argue anywhere that even the choice of models, such as picking logistic regression, could have unfairness implications?
Yeah, so we did talk about it at the beginning. So we talked about like why do we do this like decision point model type? So like there's a concern like model expressiveness because logistic regression is so simple and has these assumptions that if we violate those assumptions, that we might be introducing new types of harms. But we sort of have the explanation that like, well, the original paper that uses this data set used logistic regression, so we think it's okay, but it's not perfect. But I think that's a good point to mention that like if you sort of violate these assumptions, you might be missing.
For example, traditionally statisticians and other people not real familiar with machine learning or automating algorithms would choose logistic regression because it's simple, with no concern for how far those fundamental assumptions are violated.
Yeah.
For all kinds of things. And so, anyway.
I think one thing is like,
you answered my question.
I think like situations like this, like interpretability is like highly important. And so like there's Cynthia Rudin, I don't know if you're familiar with her, she says like in like high stakes situations, you shouldn't be using like a black box model. And so I think that's also one of the reasons we want to go with logistic regression is just because like we do care about that interpretability because it makes it easier for a doctor to come in and say like, hey, this isn't right. Like this feature should not be this prominent.
That's right.
Yeah.
But at the same time, that seems to me to sort of swing the other way. For example, that would bias somebody against using, say, a neural network or a deep learning model because it's difficult to interpret what it's actually doing, when in fact that might be the best model to use.
Yeah.
So how do we address that, the sort of counter swing in thinking, well, interpretability is useful, but shouldn't necessarily be a major decision point necessarily. You know what I'm trying to say?
Yeah. Like how do you sort of deal with that? I guess like, I mean, this discussion happens a lot. Like there's this trade-off between interpretability and the like, predictive performance of a model. And it's like in some cases you really care about the predictive performance, but in other cases you really do care about like interpretability. And I think it's really think about that context of like when do we care about interpretability versus when do we are willing to accept like trade-offs in performance for more interpretability.
Right.
Yeah.
Okay.
Any questions or?
Yeah. No, I'm definitely getting something out of it. Oh yeah, this is weird because I think before when I was running this, I was getting a difference on race, but now it's not for some reason. This looks fine, right?
train, counts, these predictions.
Could be like I just ran it in a weird order.
Let's see. I guess.
That's good. Yeah. Oh. Just a problem.
That's the problem.
What's going on with the model?
Huh?
What's going on? Why is the model that bad?
Let's see, was it
Maybe I coded the model wrong.
exercise bread? Oh, because this is the imbalanced data set. So if you do like extreme bell.
Oh, okay.
Yeah, because the data set was heavily imbalanced. And so if you're doing that like 80-10 split, then the model just learns to like just spit out.
Oh god, that's terrible, man. And then you want to do it on the balance test too?
There's no balanced test data set.
Oh, it's just the regular test.
Yeah.
Okay.
So this sort of
Yeah.
same by
See,
group.
that unbalance will get you every time.
Yeah.
Every time.
There you go.
Okay, so that's easy.
Yeah.
Yeah, this is cool. And I could pass it like a list of different protective features, right?
Yeah, so you could do something like,
Yeah. Then add in gender and age, I guess.
so yeah, so age. I think age actually shows an interesting one.
Yeah, I looked at gender. I didn't get anything, but that was on the old model, I guess. Yeah. God, isn't it funny how like they'll just misclassify everything? It's just like cool.
Yeah. And so you can see the breakdown by gender, age.
Nice, yeah.
And I guess the big challenge of like when you have an output like this is how do you actually like get something meaningful out of it?
Right, and you
Yeah.
know, like especially with a table like this, like how do you highlight? I mean, anytime that you can visualize this is obviously better.
Yeah.
What's strange to me about this is like other and unknown are in the same category, or aren't the same category because they sort of capture the same thing. Like you think of the data generating process for both of these is probably pretty similar. Right?
Kinda,
So
yeah.
I would collapse those in the same label.
Yeah, and that's something you could do above. I mean, like we said, like we chose to do this like one because it's the same thing the original authors did, and two, it's like it also like I kind of need like there to be a difference between the groups in order to do the rest of the tutorial. So it's like kind of a convenience thing of like I chose this decision because it makes things like look nice later on.
Right. Yeah. No, this is but then plotting I think is the right way.
Yeah.
You probably like implement this as part of like a validation check on a model. So it's like
Yeah.
So you want to do the visualize on the dashboard for the model,
Yeah.
which I guess we're going into, right? Or no, we're going into mitigation, right?
Yeah, so next up is mitigation. So like in terms of visualizations, like I guess visualizations are important for reporting tasks, and so like sort of showing the performance of the model across fairness groups, and that's actually something we'll be doing later on once we do the mitigation step. It's sort of like creating that visualization, showing the performance in the mitigated model, and then saving that for our model card. I do think if you do want to plot this one though, you might have to change up something here. I just don't remember what it is in the plotting because it's assuming one category.
Or not.
Yeah.
Shows you source data. So you can see here, the true positive rate is the same as just another term for recall.
Yeah.
So the recall score is the true positive rate.
Yeah.
We had to do any math, and we're like, wait, no. Fairlearn
Yeah.
defines all those metrics.
It's also imported at the beginning of the notebook that all the function. Yeah.
No, I think we already imported those. We said from Fairlearn import. Fairlearn metrics, we imported those.
Yeah. I guess if you want to use like other metrics like F1 score that are available in scikit-learn, you would have to import those if you want to use them here, but you can use them.
This is the metrics here. We just put the exercise metrics. true is y test and y pred would just be y pred.
Well, so this is for the exercise model. You should have a slightly different name for it, I'm assuming, if you scroll up a bit.
Okay.
Yeah.
Yeah,
Yeah, you have exercise pred for,
oh yeah.
yeah. For white pred.
So for y pred, instead of y pred there, it's going to be exercise pred.
And then since the features, you can pass in race, you can use race, you can look at race and gender, race and age.
So I heard him saying something about putting in multiple ones. How?
Yeah, so for example, you can do DF test, let's do race, and let's do age. And so you literally just pass it in like as a column like that, and I guess this is gonna yell at us because of the bracket. So you just pass it in like this. No. DF test, waitress.
We need exercise tests.
No, it should be something is 502, 581. Huh, it's missing some one off by one. I'm not sure why.
Maybe my split is incorrect.
See if just race works. Oh, this is X train. It should be X test. Also, you're going to run into a problem here. So, because if you just use the unbalanced data set, it's just going to learn to predict zeros. This is the trick that caught someone else. And then we don't need to change this. Let's see if this works now.
We've run into this where in insurance, trying to predict really big claims, they're very rare. So then we had people build models and we get 97% accuracy. It's like, yeah. Because there's
Yeah, and so now when you do race and age, you can see actually that broke down by the different groups like this.
And then the other metrics like the or like the differences in the ratios that's calculated for.
Yeah, so if we do like here, it's easier, and we do say metric frame exercise. Difference. And so it's just going to show the maximal difference basically by this broken down group. And so it's like, you just have to figure out what like the max and min is, but like, and it's probably going to be this 0.00 minus point, yeah. So like recall 0.74 minus 0.00 is that difference here. But you can actually, I mean, you have to sort of tweak it a bit in order to get disaggregate. So if you want to look at like, what is the maximal difference within a group, for example. So if like, what is the difference between the maximal difference in the age group? So like 0.55 minus 0.634, you just have to tweak this a bit, but you can do that.
You just pass in steps that you're passing the metric frame.
Yeah. Like, because it's like built on top of a pandas data frame, so you just have to unstack it and then do that. Cool. Okay, so hopefully everyone's had some time to play around with the metric frame API. You were able to train a model. You were able to sort of pass in a new dictionary of metrics and able to generate some results. And so one thing, also thing is worth mentioning is that remember to pass in the balanced training data set and the balanced training data. Because if you pass in the raw unbalanced data set, you're just going to probably get a model that just outputs 0 all the time because the data set's so imbalanced that, just output 0 and you get 90% accuracy. What is machine learning? So simple. Output 0. And so here we would define our metrics. As a cheat code I forgot to mention is that all the metrics were already imported for you at the beginning. So you just have to put the name here, just copy the name, and then create your metric frame. Look at by group to sort of play around the differences by different racial groups. And like as I mentioned above, one thing you could do here is actually look at the intersection of different demographic groups. So you could look at race, you could look at age. And one nice thing about the metric frame is that it actually does have it within its API that when you pass in multiple sets of features, it does do this aggregated breakdown for you very easily without really needing to change the code. And then finally, we could play around and generate a visualization. And so you can produce results like this. And this allows you to produce an easy way to sort of convey any fairness-related issues to end stakeholders of, hey, here's our model performances. Look at these visualizations. We think we might have some issues here because of this disparity in these metrics. And so now we've sort of played around with actually training a model. So now at this point, we've trained a model. We've assessed our model using the metric frame for fairness-related issues. Something exciting is going on there. We've assessed our model for fairness-related issues, and we found that, hey, when we had that untrained logistic regression, we noticed that there was a much lower selection rate for individuals with the racial group unknown, and we also noticed that there was a much higher false negative rate for that individuals with that racial group unknown. And so we believe that our model, the unmitigated model, does produce some fairness-related harm because it is producing this allocation harm where it's not recommending those individuals for this high-risk care management program, even though they would greatly benefit from this. So what can we do at this point? And so in addition to providing tools for measuring fairness-related harms, Fairlearn also has algorithms for mitigating fairness-related harms or provides strategies for mitigating fairness-related harms. And one thing to keep in mind is that we're currently thinking about the training stage of the AI lifecycle, but mitigations should not be limited to this stage. And we've also discussed different strategies that you can use at other stages of the AI lifecycle, such as checking for constructability, also thinking about whether we want to collect more data, and think about how you can sort of collect new data. Sort of, if we don't believe the data set we have is worth using for our modeling task, can we go out and collect a new data set that we think is better for our modeling task? And I think that's a very important thing to think about. In responsible AI, there's this idea of don't build it or just don't build it because it's inherently harmful. And I think it's worth thinking about in the modeling task and the task definition, is this machine learning task actually worth something that we should be doing, or is it inherently harmful? And so now going back to this idea of the model training stage, really, unfairness mitigations really occur at 3 different stages relative to the model training. So they occur at pre-processing. So before a model is even trained, you apply some mitigation algorithm to transform the inputs to the training data. So for example, some strategies, which is available in Fairlearn, but we'll not be discussing at this time, is to sort of remove correlations between our input features and our sensitive features. So just sort of correlation, like a correlation remover, sort of reduce the correlation between your input features and your sensitive feature of race. You can do things using just simple correlations. You can use information theory to do this as well, to reduce the mutual information between your input features and your sensitive feature. You can do an at-time training mitigation strategy. And so what happens in at-time training is you have the model training process. You have model, when it's being trained, it's sort of optimizing for some objective function. But we can introduce a fairness constraint as sort of like a regularization term. Think about regularization when you do regression, for example. You have that L1, L2 penalty, ridge regression, lasso regression. And you can introduce a fairness constraint like that. So now during the optimization stage, it's now trying to maximize the accuracy while trying to minimize this fairness, satisfy this fairness constraint, or mitigate this unfairness during training time. And so now the model during the training process is trying to handle this trade-off between how can I get something that's really good and predictive without producing a model that is too unfair during training process. Final thing we can do is a post-processing. So after you have a trained machine learning model, and this is a fairness unaware model, such as our logistic regression, what we can do is take that model's outputs, apply some transformation to those outputs in order to satisfy some fairness constraints. And so we have our outputs of our logistic regression model, and if we have access to our sensitive feature of race during prediction time, we could then calibrate the model's outputs in order to specify some race-specific thresholds. And so we say the probability of being admitted to this high-risk care management program, given that you're black, has to be above this threshold. On the other hand, if your racial group is unknown, then your probability of being admitted to the program just has to be above some other threshold before we admit you. And key thing about that is that when you want to deploy strategies like that, you really need to be thinking about the context. In some scenarios, for example, you're not allowed to apply race-specific thresholds for different groups. And so now in this section, we're going to sort of dive into two different algorithms. First is a post-processing approach, in which case we're going to take the logistic regression model we trained and sort of apply some transformation to its outputs. And the next thing we'll do is this specialized reductions approach, which is this train time algorithm. And both of these are implemented sort of as meta-algorithms. In the sense they act around a wrapper around any sort of standard machine learning algorithm. So if you have a machine learning algorithm that has a fit, a predict, and a predict probable function, that's very common in scikit-learn, but also in Keras and PyTorch as well. You can just pass in those models directly into the Fairlearn API to apply these mitigation strategies. So now, first thing we're going to do is sort of post-processing with the threshold optimizer. And so post-processing techniques, as I mentioned, are sort of unfairness mitigation algorithms that take in some already trained model and the data set and apply some transformation to the outputs of the model to satisfy your fairness constraints. So we have our trained model, we have our data set, and then we can apply some transformation to the outputs so that we can sort of reduce the unfairness of our machine learning model. And this may be the best thing you can do when you're in a situation where you can't actually influence the training of the data set. And so this happens a lot when working with government agencies where they hand you some trained black box model. You're not allowed to influence the training or the retraining of that data set. You just have this black box model. What can you do? You can apply some transformation to its outputs in order to make it more fair because you can't directly influence the training of the model itself. And within Fairlearn, we'll be using this threshold optimizer algorithm, and which follows from this approach listed in this paper written in 2016 by these three authors, Harth, Price, and Sebero. And how the threshold optimizer works is it takes in some existing, possibly pre-fit machine learning model whose prediction is sort of acting as a scoring function, and it identifies separate thresholds for each of our demographic groups in order to satisfy some, in order to optimize our performance metric, in this case balanced accuracy, while being subjected to some fairness constraint, in case where we look at the false negative rates, and so we'll be trying to satisfy this false negative rate parity. False negative rate parity means that we want the false negative rate for all groups to be roughly equal, so we want the maximal false negative rate difference to be approximately 0, so that is really no difference in the false negative rates across all groups. And so to instantiate our threshold optimizer, we're going to pass in three things: our existing estimator that we want to threshold, our fairness constraint that we want to satisfy, and the objective function we want to optimize. And so here we have the threshold optimizer. And if you look at this API, it's very familiar if you've used scikit-learn before. So we're going to call the threshold optimizer. We'll pass in our estimator, which is that unmitigated logistic regression pipeline we trained above. We'll specify our constraint as this false negative rate parity. As I said before, this is trying to make sure that the false negative rate difference is approximately 0. So each demographic group has 0, sort of has the same false negative rate. We're going to pass in our balanced accuracy score as our objective. So this is the performance metric we want to optimize. We'll specify prefit is true, which means that the model is already prefit. And the predict function is going to be predict proba. So this gives us access to the model probabilities rather than just the binary outputs of 0 and 1, because it allows us to create those group-specific thresholds by saying the predict probability says, like, it gives us the probability of saying 1 or 0. And thus we say if that probability is above some threshold for this racial group, then we convert this into a 1, or else it's going to be a 0. Does that make sense? So we instantiate our threshold optimizer. And one thing to note is that when we call the fit function with the threshold optimizer, we're not going to pass in both. Not only we're passing in the training data and the training labels, but we're going to pass in our sensitive features here as a train. And so now when we call the training process, you also have to pass in these sensitive feature labels. We've trained our models. And also when we call the predict function, we need to pass in our sensitive features. And so when we call the predict, rather than just passing in x test, we pass in x test and our sensitive features a test to get our model predictions. And then once again, we can create a metric frame in order to evaluate the performance of this threshold optimizer. Give it some time to run. And I should mention that as one key restriction for using threshold optimizer is that you do need access to sensitive features during testing time. So once the model is deployed, it needs access to the sensitive features during prediction time, or else you can't use the threshold optimizer. And that could be a very huge restriction in cases where you don't have access to the sensitive features during prediction time. This is also the case where you don't have access to the sensitive feature during training time, but that's a very different concern. And now let's see how well our new threshold optimizer unfairness mitigated model compares to our original model. And so here we sort of have a comparison of the two. So we see our three metrics of interest of the selection rate, the false negative rate, and the balanced accuracy, broken down by performance by different demographic groups. And key thing to note is that the balanced accuracy across all groups is relatively the same across both the unmitigated model and the threshold optimizer. It's 0.597 to 0.58, 0.54 to 0.59, 0.584 to 0.579, 0.536 to 0.572. So the balanced accuracy in this threshold optimizer or this unfairness mitigated model is relatively the same. So we're getting the same predictive performance. But the key thing to note is that the false negative rate is much lower in the threshold optimizer. We're sort of getting the false negative rates to all be around 0.38 or 0.4 compared to the original model where they were much higher. And we also see that the selection rate is a bit better for the threshold optimizer as well. So in terms of allocating benefits, the threshold optimizer is a bit more fair. And in terms of preventing harms, our threshold optimizer is a bit more fair without sacrificing predictive performance. And I think that's a big part, because when people usually talk about this making models more fair, this is the idea of this accuracy performance trade-off, of accuracy fairness trade-off, that somehow in order to make a model more fair, you have to sort of make it less good as a predictive model. And that's not really true. You can sort of make a model more fair without really affecting the accuracy in a significant way. And this is an idea I'll come back to later on in the tutorial. And now we can also compare the difference, zoom in on the difference between the largest and smallest values. And so we see when we look at the false negative rate difference difference across the unmitigated model compared to the threshold optimizer, we see that the false negative rate difference goes down from like 0.24, so 24% false negative rate difference, down to 0.05. We also see that the selection rate difference goes down as well, and that the balanced accuracy difference goes down, but it doesn't really appear to be meaningful. Different, like 0.06 to 0.02, not that big of a deal. And so as I said, like we see that the threshold optimizer was able to substantially decrease the difference between the values of the false negative rate across all our different racial demographic groups. And finally, we want to save this model. We can visualize this model's performance, and we can also save that figure for later evaluation. So here we can see the visualization of our threshold optimizer and broken down by the different racial groups for each metric. And we see that the false negative rate is much more similar across all four racial groups, and the selection rate is also much more similar across all four racial groups compared to the original unmitigated model we trained above, where we noticed that there was a big difference in the selection rate and the false negative rate between unknown racial group and the other three racial categories. And so now, as a small exercise, in this exercise, we'll sort of go through this task of creating our own threshold optimizer. And we'll, instead of using the false negative rate difference or false negative rate parity, we'll be looking at the true positive rate parity, which is also known as the recall score. And the nice thing about this is that for any model, the true positive rate plus the false negative rate should equal 1. And so by training the threshold optimizer to achieve true positive rate parity, we are effectively producing a model that produces the same performance as the threshold optimizer above by minimizing the true positive rate difference across all groups. We're effectively doing the same thing as minimizing the false negative rate difference across all groups. And the goal of this exercise is for you to sort of walk through this exercise of getting familiar with the threshold optimizer API and sort of playing around with this idea that by minimizing the true positive rate parity, we are sort of getting the same thing as by minimizing the false negative rate parity. Does that make sense to people? Yeah, so once again, if you're using the student notebooks, you should see something like this, where you have sort of fill in the blanks. And you can go through and fill in these and then try to train a metric frame in order to get the results of the new model and compare it to the old threshold optimizer we trained above compared to your new one. So it's now 3:43, so I'll also take another 15 minutes, 10, 15 minutes to sort of play around with this of trying to create a threshold optimizer that minimizes the true positive rate parity and seeing how that performance of this new threshold optimizer compares to the one we just trained above. Sound good? Good. So hopefully at this time you all had a chance to sort of play around with the threshold optimizer API. You tried trying to do this mitigation using the true positive rate parity, and you saw that like, oh hey, it is very similar to what we got earlier from the threshold optimizer, just trying to minimize the false negative rate parity. So if we do this here, and when we do compare the two groups, we actually do see, yes, they are very similar. So this is the one we just trained, and this is the metric frame that's using the false negative rate parity. We can see like, look, the accuracy is very similar across the two groups. The false negative rate is very similar across the two groups. It's almost exactly equal. And then we see the selection rate is almost exactly equal across the two groups. Because like I said, by minimizing that false negative rate of the true positive rate parity, we're essentially doing the same thing as minimizing that false negative rate parity. And finally, let's talk about our last unfairness mitigation strategy. And so this will be using the reductions approach, and we'll be using an algorithm called the exponential gradient. And so with the threshold optimizer, what we did is we took a fairness-aware, unaware model, and we applied some transformation to the model's outputs or decision boundary to satisfy our fairness constraint. We applied some transformation to the model's outputs in order to satisfy that false negative rate parity or that true positive rate parity. Now, one big limitation of that threshold optimizer is that we really needed access to our sensitive feature race at prediction time. Like we needed both, we needed race both at the training time, but also at prediction time when we call that predict function. And that is one key limitation. And so what can you do if you don't have access to your sensitive feature at prediction time? And so in this section, we'll be talking about how we can use this reductions approach from this paper, Agarwal et al., to obtain a model that satisfies the fairness constraint, but doesn't necessarily need access to our sensitive feature race during deployment time or during prediction time. And so this terminology reductions refers to another kind of wrapper approach, where instead of like wrapping an already trained model, we're going to sort of modify the training process of an algorithm. What we're going to do is we're going to take a data set, or take some model, like logistic regression, and we're going to train it on some weighted data set. And so we take the model, we take the data set, we train it, and we see how well our model does in terms of accuracy, but it also does how well it does in terms of our fairness metric. And then we upweight or downweight specific points in the data set, and then we retrain a new model on this now re-rated data set. And through this iterative process, we're going to be constantly training a model, and re-rate the data set, get a new model, predict, and re-rate the data set. Do this over and over, and we're going to produce a sequence of models that now are sort of balancing this trade-off between performance on our fairness metrics by re-rating data sets in a way such that when we optimize our model, we are now accounting for this trade-off between performance and fairness. And so the goal of doing this is that when we use this reductions approach, we also want to we're now directly during this optimization or trade-off between the performance metric and our fairness metric, but now also during at training time rather than after the model has been trained. And the main algorithm for reductions within Fairlearn is this exponential gradient. Actually, the Fairlearn package was originally created with the exponential gradient algorithm in mind, and then we sort of added on other functionality over the years to allow for more generalized fairness assessments and mitigation strategies. And like I said, it sort of does this iterative training where you take, sort of have a model, you constantly iteratively retrain it on some weighted data sets. And so now you have and this process mathematically finds a model that sort of satisfies the trade-off between performance accuracy and your fairness constraint. And so this is a nice thing because it's like mathematically optimizing the trade-off between these two. Whereas I think the other algorithms sort of do their best with heuristics. And key thing about the exponential gradient model is because we're constantly doing this re-rating process and retraining process, that the exponential gradient really learns a sequence of inner models. And during prediction time, it's actually choosing between these prediction models randomly to make some prediction. And so how the exponential gradient algorithm works is that we're going to sort of use a very similar API. We're going to pass in our base estimator. So this is some model that supports training. So this is a model with a fit function. And then we're going to pass in our fairness constraint. But specifically, we're going to use a special object called a Fairlearn moment to satisfy our fairness constraint. And this allows us to really measure the trade-off between the fairness. Allows us to really model this performance between our performance metric and our fairness metric. I guess to elaborate a bit further, like if you are familiar with how machine learning models are trained, there's this idea of gradient descent. Like there's a direction of which way to minimize the best error. And what the exponential gradient algorithm does behind the scenes, as the name gradient implies, is going to be sort of using a similar idea to gradient descent to find the pathway to best to handle that trade-off between performance and fairness. And so at each iteration of the model, or each model iteration, we're going to find the direction of best re-weight the data set to handle this trade-off between model performance and the fairness constraint. And when we pass in a fairness constraint using the moments, we also want to specify a difference bound. So this is basically what is the maximal difference for that metric we care about. So if we're looking at that true positive rate parity or that false negative rate parity, if we specify a difference bound of 0.2, that means we're willing to have that fairness constraint sort of say, rather than making these false negative rates equal or these true positive rates equal, we'll allow a maximal difference of 0.2. And that's actually one key thing about the exponential gradient is you can sort of tune this as like a hyperparameter of how much the maximal difference I would be willing to do between our fairness constraint and our performance accuracy, and how does it affect the end result model. And so when we call this exponential gradient algorithm, we pass in our base estimator, in this case is a logistic regression model, and we'll pass in our fairness constraint, which will in this case be the true positive rate parity, because as we showed above, minimizing the true positive rate parity is the same thing as minimizing the false negative rate parity. And so I'm going to let this run because this actually takes a while to do this constant retraining process of re-rating the data set, training a new model, training a new data set, and retraining a model. It's giving a mean error just because of the way it's doing behind the scenes. It's using a depreciated function in pandas. We have a version 0.8 coming out in a month or so, and so that will address that issue, but it's not fixed yet. So let this run. And one key thing about the exponential gradient, like I said, is training a lot of inner models behind the scenes and then picking one at random during prediction time. And so if we want to make the results more reproducible during prediction time, we have to pass in a random state in order to the predict function. And so now when we call predict, we pass in our test data set, and we also pass in our random seed to make sure that we're not, to deal with that randomization. So we call this. But one key thing here is that we don't actually need to pass in our sensitive features at prediction time. And so we avoid that restriction from the exponential gradient algorithm that we don't need access to our sensitive feature at deployment time. And now we get our model's performance, and we can look at the difference between the smallest and largest values. And so one key thing about the exponential gradient is that it does reduce the false negative rate. Like we went down from 0.24 to like 0.154. But the false negative rate difference is not as great as it was in the threshold optimizer. And that's partially because we don't have access to those sensitive features during testing time. So like we're sort of doing this trade-off of like not needing access to sensitive features during testing time to get a model that doesn't really handle that, doesn't really do the mitigation of unfairness as greatly as possible, but still does better than our original logistic regression model. Like we reduce the unfairness from 0.024 or 0.24 to 0.15. So that's still a 10% decrease or 0.1 decrease. And like I said here, so like I said, like the decrease in the unfairness is not as big as the threshold optimizer, but it is still bigger than what the unmitigated model had. And we were able to do this without using our sensitive features at deployment time. And so, like I said, now we can, in this section, we're going to sort of look at the individual predictors learned by the exponential gradient model. And so, like, during the training process, the exponential gradient model is sort of iteratively training a lot of inner models behind the scenes, and the algorithm stores those stores predictors and chooses one at deployment time. And in many applications, that type of randomization is undesirable. And also, using multiple inner models can pose some issues for interpretability. It's hard to tell which inner model is being used to make a decision. However, these inner models in the exponential gradient model, in the exponential gradient algorithm, sort of span a variety of fairness accuracy trade-offs. And what we can do is actually access each of those inner models and look at how they handle that fairness accuracy trade-off individually. And so here we're going to get our inner models. And you can see behind the scenes that the exponential gradient algorithm trained 10 or 11 actually, I think this is 12, logistic regression models behind the scenes. And so now we have 12 predictors we're working with. And what we're going to do, what all this function does, is basically evaluates each of these inner logistic regression models according to our metrics. And so we're going to calculate the balanced accuracy or the balanced error rate for each of these inner models. And we'll also calculate the false negative rate difference for each of these inner models. And then we can actually plot the performance of both all the inner models, but all the models we've trained so far. And so here we can see actually a trade-off between all the balanced error rate and the false negative rate differences for all the models we've trained so far. So it's not just the exponential gradient models, but also the combined model as well, but also looking at our original unmitigated model and the threshold optimizer. And we can see how we have a bunch of different models that span this trade-off between the balanced error rate, which is our performance metric, but also the false negative rate difference. And so here we can see here's our original unmitigated model in green. I don't know how you can see that, but it's doing pretty well on balanced error rate. It's like it has one of the lowest balanced error rate of all the models, but it also has one of the highest false negative rate differences. On the other hand, we can see we have other models, both inner models learned by the exponential gradient algorithm, but both the exponential gradient algorithm itself and the threshold optimizer have about roughly the same balanced error rate, but greatly lower false negative rate differences. Like, look at the scale on this x-axis. It's going from like 0.4 to 0.48. So what this is really saying is that with a slight decrease in balanced error rate, and that's really trivial, like a error increase by like 0.01 is probably not a big deal in practice, we can greatly reduce the false negative rate difference from our unmitigated model from 0.25 down to like 0.15 or down to 0.5. So reducing this unfairness from nearly 20% to like up here, this would be about like 80% reduction in unfairness. And I think this ties back to something I mentioned earlier, that a lot of times when we talk about this idea of accuracy and fairness, is this idea that there's this huge trade-off, that somehow to make our models more fair, we have to like drastically harm the accuracy of our models or destroy the accuracy of our models. But we see here that we're able to make models that are much more fair, as defined by our fairness metric, without really affecting the balanced error rate or the accuracy of our model. And I think that's a key point I want to elaborate, that I think you can actually, I guess not have your cake and eat it too, but sort of that you can greatly reduce the unfairness of a machine learning model without drastically affecting its performance accuracy. Yes? There are definitely cases where it's not true, but I like, for example, I was working with one with like financial credit lending, where you do see this big trade-off between the accuracy of the original model and sort of mitigating the unfairness. But I think there, when you think about how you do this in practice, in a lot of cases is like, what you do is you basically say like, I have the unmitigated model, and I'm going to take some, give it some like tolerance. I'm going to say like, take the error rate of this, and say, I want a model that's almost as good as this, and then filter out for those models, and then pick the best one that's most fair. And that's actually what you do in financial lending, for example. What you do in finance, for example, is you train like 20, 30 different credit models. you look at the performance metric and say like, I need, these 10 are the ones that are actually profitable according to our business model, and then look at the unfairness of them and say, of these 10 that are profitable, I'm gonna take the one that's the least unfair or has least disparate impact, and that's what you can do in practice as a strategy for that. And so even if you don't get this like, this nice, like almost no trade-off here is in this case, that's a strategy you can use in practice there. Does that answer your question, or?
Yeah, it does. No, I mean, the idea that there's many models that sort of have similar accuracy to the one that is fair.
Yeah.
Sometimes there's free lunch, so that's not.
Yeah, and I mentioned that like a lot of these small differences we're seeing here are really partially a decision of like all the decisions we made above, so like the downsampling strategy, but then also even like the random seed, where like if I change that random seed at the beginning from like 445 to like 446, we would see slightly different things, and we might not see like our free lunch that we got here just by changing that random seed. So this is definitely a bit more of a nice artifact of like everything we did, and I partially chose it because it produces a nice like output for a tutorial. But you really don't see that like free lunch that we got in many other cases.
Does it also, like, in terms of the pipeline,
I can't hear you because they're yelling.
other feature transformation options that can adjust the fairness as well, or is that an automated process?
You mean by like feature transformation? So I mean, there are things that you can do to remove the correlations, and there's an idea called admissible ML, which is the idea is like how can you sort of take a machine learning, like how can you use information theory to learn a set of features that have low mutual information with the sensitive features, but still have high predictive accuracy, so high mutual information or conditional mutual information with your labels. And so that's one way you could do that, is still learn a feature set that's still predictive of the label by having high mutual information there, but having low mutual information with your sensitive features, and so that handles that trade-off there in the transformation of the data.
No, is that an automated process though? Because I'm thinking of like, suggesting certain feature transformations that have that property that we're describing.
So there are other libraries that automate this. I know H2O AI does some automation for this, but we don't have that in Fairlearn, partially because it's also counterintuitive to our fundamental principle that fairness should always be socio-technical. Like, I think there's this danger of like, how do you, if you automate things and really don't think about like the context of fairness, that you're sort of going to miss some important societal context. And so, is a way that you can automate this, but we just generally don't encourage it.
No, I guess I'm not suggesting like it makes decisions without your awareness. What I'm saying is like it suggests certain feature transformations, like as opposed to doing this type of centering and scaling, this other type of like min-max type operation.
So I don't know anything that's specifically like that. I think there are some like data platforms like Dataku that has some fairness suggestions that they recommend to people, but I'm also not very familiar with that because it is like an enterprise platform that you have to pay for. Yes?
Just to build on the first question, are there describable characteristics of a data set that make it more amenable to like being able to be more fair without a reduction in accuracy, or is it really just like just try and see?
It's definitely a characteristic of, I mean, it's like, one is the context of the problem itself, because actually there are many cases where the strategy to make the model more fair actually has nothing to do with the data set or even in the machine learning process. A good example of this is that they were using machine learning models to determine who gets SNAP benefits, so food stamps eligibility in Southern California, and it turns out like the model discriminates against people who are Hispanic because they didn't speak English as well. And the solution was just to offer the forms in Spanish. And so it's like a non-technical strategy or mitigation strategy that greatly reduced the unfairness of the model. But I think going back to your question of like data set collection, I think one key thing that we really talk about with data sets is like, how do you get a good data set? Like, how do you collect a data set? And that we don't really talk a lot about machine learning. We sort of just like grab a machine learning data set off the shelf and really don't think about those when we think about these fairness issues in the data set collection process. So I think one thing that people think about is like, how was the data set collected? And that will probably lead to fairness issues downstream. Yeah. Any other questions at this time? And so at this point, we've sort of trained a bunch of, we trained an exponential gradient model, we trained a bunch of inner models, and we got that, got these results. And so in this final exercise, and this will only be, let's say, 10 minutes because we're coming close to time, we can think about how changing the base model for the exponential gradient sort of affects the overall classifier. So when we did the exponential gradient, we passed in a logistic regression model. But what if we pass in a different model? And so here we can pass in this histogram gradient boosting classifier, so that gradient boosting tree we use in an above exercise, and sort of see how that affects the model as well. And one thing you can also do is if you want to play around with the difference bound. So rather than using the difference bounds of 0.2, you could try increasing this to 0.05 or decreasing to 0.01 and see how that affects the exponential gradient learned as well. And I think go through the same process that we just did above of sort of creating a new exponential gradient model, fit it to the data set, compare its performance, but then also pulling out the inner predictors and sort of going through them and plotting those results. And so like I said, I can give you 10 minutes to sort of go through this process because the exponential gradient does take some time to run, but this will give you some opportunities to play around with this model and see what kind of results you get by changing the inner model and possibly changing the difference bound if you want to. Okay, everyone, so we're coming at about the last leg of our tutorial. Hopefully you had some time to play around with the exponential gradient algorithm. You probably got a bunch of the error messages. But what you can do is you train the algorithm, and you can see how it compares to like our original model and sort of compare the performance of the two. And you see that they're very similar, but that there is some effect of the this on the prediction of the models and both the number of inner models learned, but also the performance of those inner models as well. And so finally, we're going to come around to this wrapping up of what we've done. So we've gone through this entire process. We've taken a data science task from the beginning of this healthcare scenario. We've talked about whether the task itself is worth doing and whether the data set we were using is appropriate for our task. We've then trained our initial logistic regression model. We then assessed that model for fairness-related issues using the metric frame. And then finally, we talked about two unfairness mitigation strategies in the form of the threshold optimizer and the exponential gradient algorithm. And so now, in this final section, we're going to sort of wrap up and look at, sort of do an overview comparison of the different things we've looked at. And so one thing we can look at is sort of how does our model compare, our three models compare across their different metrics of choice. And so all this have here is just like a different, some nice helper functions that will plot the comparison of, or visualize the performance of our models across our different racial groups. And so we see here for the false negative rate, we see that the unknown false negative rate is much higher in the unmitigated model compared to the other groups, whereas on the other hand, when we do this, whereas when we look at the other racial groups and other features in the other models, we seem to get very similar performances. And so in addition, we can also look at balanced accuracy, and I think this is the very interesting one, where we see that the balanced accuracy across our groups is relatively the same across all our racial groups, across all three models. And so what this means is that in both unfairness mitigation strategies, in the threshold optimizer and the threshold optimizer and the exponential gradient, we really don't see a drop-off in balanced accuracy. We're able to sort of make models that are more fair or reduce the unfairness without really harming the balanced accuracy of our model. So we still have models that are still good predictors or as good predictors as our original models without really affecting the performance or accuracy of them. And finally, we look at the selection rate, and we can see that across all groups, that the selection rate of the post-processing algorithm is actually higher across all groups. What this means is that the threshold optimizer is outputting one more. It's basically recommending people more for this program. And that kind of makes sense, because in order to reduce the false negative rate in such an imbalanced data set, we have to output that label one more. We have to recommend more people to this program. So we get this output that we see here that it sort of makes sense that both the reductions algorithm, the exponential gradient, and the threshold optimizer have much higher selection rates in that they're more likely to recommend people for this care management program. Finally, another thing we can do is sort of compare the overall performance of the models. So here we looked at the model's performance broken down by different racial groups, but we can also compare how the model is doing overall. And we see just like the overall performance that, once again, the balanced accuracy across our models is relatively the same, but the false negative rate is actually much better in the post-processing algorithm. The overall false negative rate in the post-processing algorithm is better than the unmitigated one. And again, so we see that the selection rate for the post-processing algorithm is higher than the selection rate for the unmitigated algorithm. So overall, this post-processing algorithm is allocating its benefits more and reducing the harms just overall to all people without really affecting the accuracy. And finally, we can look at those the differences in the model. So we look at the maximal differences across all three metrics. And here we can see really the big difference in our models, that the selection rate difference, the false negative rate difference, and the balanced accuracy difference is much higher in the unmitigated model compared to the other two. That this unmitigated model has much higher differences across the racial groups for all three metrics. On the other hand, the post-processing algorithm has the lowest differences across all three metrics. And so this model is, like I said above, is not really affecting the overall accuracy of our models, but is also reducing the unfairness across these three relevant metrics. And we see a similar trend for the reductions algorithm or the exponential gradient algorithm, but just not as extreme as the threshold optimizer. Once again, this is sort of that trade-off we make of the threshold optimizer needing access to sensitive features at prediction time, allows it to do a much more powerful reduction in unfairness, but the exponential gradient algorithm doesn't necessarily have that restriction of needing access to sensitive features. So one thing I want to touch on is this idea of randomized predictions. And so both these exponential gradient algorithm and the threshold optimizer yielded these randomized predictions that they may result in different results given the same instance. I actually didn't touch on it too much for the threshold optimizer, but for each group-specific threshold, it's actually learning a pair of thresholds and saying, like, if race is equal to black, 70% of the time I'm going to use this threshold A, 30% of the time I'm going to use threshold B. So it's actually doing some randomization behind the scenes. And due to legal restrictions or other concerns, we might not be able to deploy such a randomized algorithm in production. But there are ways to address this. For the exponential gradient model, we can actually deploy one of those deterministic inner models we learned. And that's what we did with like calling the predictors and looking at the predictors and possibly selecting the best one that still has a good balanced accuracy or balance or performance while still minimizing the unfairness. With the threshold optimizer, there's a way to take those randomized thresholds learned for each racial group and sort of just like interpolate the two, sort of just weight them by the probability and just average it together to get some deterministic number. And finally, one key limitation is sort of this access to sensitive features. So with the threshold optimizer, we needed access to the sensitive features or race during both the training time and the deployment time, or prediction time. If you don't have access to the sensitive features during both training and deployment, you would not be able to use the threshold optimizer. On the other hand, the exponential gradient model only requires access to sensitive features only during the training time. So you only just needed access to this sensitive feature race during our training data set, and we don't necessarily need it when we're making predictions. And so finally, in this last section, we're going to create a model card for model reporting. So we did a bunch of analysis, and we created a bunch of models. And so now we're going to create a model card for one of our models. And this is a practice we do before we put this model in production. We want to produce a documentation saying, here's our model, here's how we evaluated it, here's how we thought about the fairness-related concerns, and here's also other characteristics we want to think about before we deploy this model in production. So one caveat is that this code works well in Google Colab, but it may not work in all environments just because of how the toolkit was designed. And so the model card framework was produced by, came out of Google research by Margaret Mitchell's AI group back in 2019. And so they proposed this framework of model cards as a way of documenting and reporting model training details and deployment considerations. And so this model card document is a way to sort of highlight the training and evaluation data set summaries. So like what was the training data set, what was the evaluation data set. But it also talks about like quantitative performance, such as that fairness evaluation we did. And we can also highlight some ethical considerations about like, hey, here are some concerns about the model. Here's when you should use this model. Here's when you shouldn't use this model as well when we create the model card. So what we're going to do is we're going to call this model card object. And in the first section, we're going to sort of fill out some model details. So we're going to fill out things such as the name of the model, a brief overview, description of like what it is and what is it meant to be used for, summarize some owners, so who owns the model and what's their contact information, along with other information such as licensing and version as well. And so here we have all this information about model details such as name, overview of like what the model should be used for and what it's supposed to be used for, owners, and then license and versions. Next, with model cards, we can talk about the use cases. So talk about like when is this supposed to be used for? So this is in our case, we talked about like, this is meant for like high-risk patient care management. And who are users of this? So this is medical professionals in the hospital, but also machine learning researchers. And then we also talk about limitations. So I think this is a key thing, because like when we report machine learning results, we usually talk about the positive. We talk about, oh, we've trained this machine learning model, and you can use it for practically everything, because that's how you generate hype for your product. That's how you get people to use your product for any case. But I think it's important to specify our limitations. We sort of understand that a model can't really generalize to every scenario, and we want to talk about when it could not generalize. And so in our case, our data set really came from US hospitals, and so we don't think it can generalize to hospitals outside the United States. And certain features, such as those encoding insurance information, are inherently tied to the US healthcare system. And we might also want to highlight some ethical concerns, such as like the low sample sizes of certain racial groups could lead to lower performance on these models. And we can also highlight what could be some mitigation strategy for that ethical consideration. So we believe this ethical consideration exists, or this ethical concern exists. What can we do to minimize that ethical concern as well? And in the next sections, what we can do is sort of talk about the training data as well. So we can basically pass in some information about the training data set. So we can say the training data set was undersampled to have the same equal number of positive and negative features. We can say the training data set had this shape with number of rows and number of features. And we can pass in those information about the sensitive features and the target. We can do the same thing with the evaluation data set. And then we can also highlight our fairness concerns, so our fairness evaluation. And we can say we did a model analysis on a test data set to do some disaggregated evaluation and highlight those as well. So it'd be the model performance, but also some visualizations as well. And then finally, we can compile the model card. And when we do this, we get a document that looks like this. So this is the HTML version. And so you can see here all the sections of the model card, such as the model details, which is like an overview of it, a version, when it was produced, some references to the original data set, the use case we care about, some limitations, some ethical concerns, but also we can see the data set summaries of the training data set, so the sensitive features within a training data set, and also the label itself, along with the sensitive feature and the label distribution in the test data set. And finally, with quantitative analysis, we can see our performance of our metrics of the false negative rate across our different racial groups for the threshold optimizer we trained. And we can visualize the performance as well. And so with the model card toolkit, you could export this as a PDF document. And so when you produce this document, train your model, you could produce this documentation alongside of it. It says, here's my model as like a pickled artifact, but here's this PDF document summarizing the model itself and how it was trained and evaluated, along with those fairness concerns that we evaluated for. And this is a great way to communicate with external stakeholders. And so non-technical stakeholders, you can sort of highlight, here's the testing we did, here's the things we considered, and the medical expert or some other domain expert could come and say, like, hey, have you thought about this thing or thought about this other thing? And they can provide you guidance on what other further fairness testing you can do based on this model card. Yes? Yeah. Yeah, so something you can do, specifically in the limitations and ethical concerns, you can highlight those mitigation strategies and what you did. There are other sections that are not used, I'm not using the model card right now, but are available to highlight sort of like, here are the things we looked at, here are the things we care about. And for example, for these mitigation strategies in finance, you need to prove that your model is, that when you deploy a model, it is like the most, it's still profitable while still minimizing the unfairness of it. And so in that case, those financial institutions have a lot of documentation basically showing this, because if they're ever taken to court, they can say, actually, no, Your Honor, we did all these evaluations of these 20 different models. Here's how we evaluated them, and here's how we try to address this fairness-related issues. But we may not be able to do this perfectly while maintaining profitability. And so model cards do allow for that, and this is actually very, very tied into how a lot of regulated industries have to do this and report these documentations as is. And so now we've produced our model card, and we come to the end of the tutorial. So in this like three and a half hours, we've sort of talked in depth through this healthcare scenario through all different stages of the AI lifecycle, except for the model deployment. So we've talked through the task definition, talked through the data set evaluation, we talked through the model training, and then also the unfairness mitigation. And the last step is sort of actually deploying this model in practice. But we've also seen how like fairness-related harms can arise in these different steps, such as poorly defined task definition, poorly defined data collection, or really not thinking about fairness-related issues in model training and evaluation. And we've talked about different tools you can use for fairness and responsible AI best practices, such as datasheets, Fairlearn, and also model cards. And one key thing, since we really didn't talk about model deployment, is that even after a model is deployed, it's important to continue monitoring our model for key metrics to assess any performance differences, as well as potential new fairness-related harms you didn't think about. So after you put the model in production, it maybe turns out that some new fairness-related issue arose that you weren't thinking about when you were creating this model. And an important thing about after your model is deployed is I think it's important to think about like fairness as like this ongoing process. I think a lot of times when we talk about AI fairness, we talk about this as like one and done thing. Like you have your model, you apply some unfairness mitigation strategy, then you're good to go. Whereas it's a continuous process of you're going to need to like continuously evaluate your model for new fairness-related issues, and I think that's really ties into this idea of ML ops of like how do you monitor these models when they're in production, and how can you take these models off a line very quickly if a fairness-related issue arises or is discovered. And although we have used a variety of software tools, fairness is inherently the socio-technical challenges, so our mitigation strategies cannot inherently be purely technical, and they need to be supported by practices and processes, including organizational incentives and government regulations as well. And by organizational incentives, I mean if you as a well-intentioned data scientist want to do things like this, but your boss doesn't really give you the time to do it or reward you for doing this work, you're probably not going to actually do it. And so I think in order to get like fairness and responsible AI in a business practice, you need to have it coming from the leadership team. They need to allocate headcount, they need to allocate training, but also reward people for doing this type of work. And if you would like to learn more about fairness of AI systems or contribute to the Fairlearn package, we would welcome you to join our community. Fairlearn is built and maintained by contributors from a variety of backgrounds, from expertise, and we come from different parts of the world, from like North America, but also Europe, and we also have some individuals in our community from Asia as well. And further resources can be found on our website. And so I hope you really enjoyed this tutorial and you got something out of it. I promise we're very friendly people. We also have a weekly community call on Discord. So if you are interested in getting involved with the community, check out the package on GitHub, but also join our Discord community. And if you have the time, maybe you can join our community calls. I'll stick around for any questions anyone has, but it's time the tutorial is done. I hope you enjoyed it.